Was that a thumbs up to go? Okay, yeah, so let's get started. Hello, everyone. Hope you had a good break. My name is Shawn. I'll be here the whole academy, so you'll have lots and lots of time to spend and talk to me, and hopefully some presentations as well. I'm notorious for speaking quickly. I'm sure all of you who've seen my videos know that. I will try my best to speak as slow as I can, but I get excited, and when I get excited, I just start talking. I definitely encourage anyone here to just stop me, ask me to repeat something, ask me to say something again, whatever it needs for you to understand. But yeah, I mean, I take no offense. I know I speak quickly. Please slow me down. I think I wanted to start by giving a little bit of context. I just feel like we missed at some point just giving context. We started giving presentations. We didn't tell you what's going on, right? So the academy used to be a 6-week program, right? 6 weeks of intense training. You know, you go and do this thing nonstop, right? But I think 6 weeks is a long time for anyone. I mean, even 3 weeks right now, you're here dedicating for the academy. 6 weeks was a long time for getting people like to stop their jobs or to leave their schools or their families and to be in the academy, right? So what we tried to do was we tried to split the academy into kind of 2 parts. The PBA X, which was kind of trying to teach you all of the basics, the fundamentals, and then this in-person PBA, which is going to go like hardcore into the deep stuff, right? And so after these first 2 days of fundamentals, you can expect that we're going to have these two tracks, the protocol track and the DApps track, and we're going to be going hardcore into things that you would have gotten in the last academy multiple weeks into the program, right? So we're going to get you through things faster. That being said, this fundamentals, these first 2 days was all about just recapping for you the information that we expect everyone to know that's relevant for both the DApps and the protocol track, right? So things like scale encoding, you're all going to use it. The runtime, metadata, all of this is relevant for all of you, right? And kind of when we were thinking about, okay, well, what is the ultimate way to ensure that you have a fundamental understanding of what's going on in this space? What topics should we go over? What things should we teach you? And the number one thing we can teach you, and in my opinion, to cover your knowledge here is light clients, right? So of course, all of you are interested in blockchain. This is like a kind of a blockchain academy, but learning to build a blockchain isn't anything super special. It's just a distributed ledger, right? It's some kind of, you know, redundant system. A blockchain by itself really doesn't do any of the things that it promises to the world, right? Blockchain by itself is just a technology. It is not itself Web3. If you want to really understand what makes blockchain technology elevate to this Web3 promise, to this future of less trust, more truth, that is where you have to go to light clients. And so before I even start, I want to show you 2 things. This is the Bitcoin white paper. Who has read the Bitcoin white paper? If you haven't, you should. It's super simple. It's incredibly amazing how concise and well-written this is. And again, I mean, you should read it and you'll see kind of like the genius behind Satoshi, right? But even in the Bitcoin white paper, here on section 8, he describes light clients. Oh, wait, make sure I'm not muted because I hear my voice. Okay, yeah. I turned off my audio. Okay, anyway, let's go. Let's make this bigger. That even in Bitcoin paper, the very, very, very first blockchain, right? He had put this as its own section. It is possible to verify payments without running a full network node. This node would follow the block headers of the longest proof of work chain, and by querying and using things like the Merkle tree, be able to prove that your transaction is included inside of the block, right? So even Satoshi at that time was thinking about light clients. And if we go to the Ethereum white paper, exact same thing. That there's an entire section here, a protocol known as another class of nodes to exist called light nodes. These download the block headers and verify the proof of work for the block headers, right? So light clients is a fundamental part of not just making blockchain technology work, but making it Web3, making it accessible to everyone. So what I'm going to go over in a few lectures, I have 5 parts here, is discussing what is a light client, how it works, why it is part of the Web3 fundamentals, and kind of, again, end-to-end, assuming you want to use a light client, make a transaction to a blockchain, what does that look like? And it touches on all these different pieces, some of which you know, some of which you'll learn more in the future, okay? But I want to get away here. Like, really, the light client is the fundamental thing that takes blockchain and makes it Web3, right? A blockchain by itself is just some distributed ledger, and that's not that exciting. Okay, so let's get started. Part 1, what is a light client? So As we said, blockchain systems are decentralized and trustless because anyone can verify the full state of the blockchain and look at the history and verify that all of the state transitions were done correctly, right? The most common way that you verify this is by doing re-execution. So like most of you all are familiar, like I basically have a block, I re-execute all the things, and then I get the final state, and I match that final state with all the other state of the network, right? Of course, with modern technology, we have things like ZK proofs, so you don't necessarily have to re-execute everything. You can actually have other ways of verifying the state of the blockchain. But the ultimate thing is that we're able to kind of trustlessly understand or follow along the block because we're able to independently verify that the things happening on that blockchain are correct, right? That is where we get the less trust, more truth. Otherwise, you're just having some server calculate something, and you have to trust that they're doing it correctly, right? That's back to Web 2. Now, one of the problems is when you have blockchain, which is having to re-verify all the things, probably by re-execution, then the speed of your blockchain is ultimately limited by the speed of your computer, right? So if you have a blockchain network with hundreds of computers around the world, right, and you're expecting all of these nodes to be able to re-execute things and run things and build blocks, right, then your network is only as fast as the computers running that network, right? So depending on what you choose as a CPU requirements, SSD requirements, RAM requirements, even the networking speeds, how close your network is together or far apart, you can get more speed. This is why I'm not so impressed with a lot of blockchains that achieve scalability through vertical scaling. What they've basically said is, hey, if we ask for you to run a more expensive computer with nodes more closely together and do all this stuff, we can make your blockchain faster. Congrats, you absolutely can. But then you make the system less accessible by the average individual. You make nodes harder to run. You make your clusters more centralized, right? Really what we want to do is create systems where anyone can go and become a node producer. Anyone can join the network. And actually, proof of work was kind of beautiful in this case. You can even run proof of work on your phone, right? Now, it wouldn't be very efficient. You would make a lot of blocks. But the idea is that anyone could contribute. But there are a lot of chains out there who are using vertical scaling as a way of basically saying, hey, we can make a fast chain. But they basically just make their system more and more centralized, right? So again, one of the things that we figured out in Polkadot, again, is that we employ a lot of, instead of just vertically scaling things, we employ a lot of very advanced engineering to achieve a secure, scalable, and resilient network, right? And the kind of way we do it is we do horizontal scaling. Again, you'll learn about this a lot in the next lectures about Polkadot, but we do a horizontal scaling to be able to get faster speeds. But that being said, even on Polkadot, we have requirements where if we made our computers faster, it would make the blockchain faster, right? So the question I think becomes then, if you have a blockchain system, right, that is more accessible, like if you wanted to that anyone could run it on their phone, will this hurt the network? Will this make it slower? Like, is this actually something that we can be competitive with, right? And so the question really is that, does the decentralized future exclude people from using their phones and accessing these systems trustlessly, right? Can we only expect people to access this network when you have a full computer, full node running at home, right? The answer is obviously no. And this is where light clients come in. So light clients or light nodes are those that do not fully execute or to sync the blockchain, right? What they do is they use verifiable proofs to communicate information trustlessly between themselves and a full node. So basically, they are some kind of small node which doesn't do all the heavy work and execution of a real full node, but has the knowledge of the blockchain and uses fancy tools, which we'll talk about, to be able to communicate with a full node, to be able to get information, but still maintain the trustless nature. It's able to verify all of the information it's receiving from it without having to necessarily re-execute everything itself. And as we mentioned, this is a very important thing. This is something that even Bitcoin, Ethereum has put into their papers. This is a key part of what we expect for the Web3 future to exist. And this is what light clients exactly do. So how do they work? As we already saw, light clients, they synchronize and verify just the block headers. So they're just synchronizing the block headers of the blockchain rather than the full blocks themselves, right? And the block headers include information which tell the light client everything they need to know to trust us to follow the chain. And we'll go over what all those information is. So let's break down the block, right? So a full block that the full nodes are handling has two parts. A block header, which has things like the parent hash, right? The hash of the block before it, the block number, the state root, extrinsic root, the digest. It also has this block body. This is a vector of extrinsics, the transactions that your block is actually going to contain. So again, the light client only synchronizes the block header. It doesn't need the vector of extrinsics. It's not re-executing anything, right? But this thing like the parent hash, block number, state root, extrinsic root, and digest, those are all key details, some of which are entirely meant just for the light client. And again, one of the things we do to identify a block is that every block can be uniquely identified with a block hash, right? So for this, we hash just the block header, right? So again, the block body has a vector of extrinsics that you see here. But we see inside the block header, there's an extrinsic root, basically a Merkle root of the extrinsics. So by just hashing this up here, we get a unique fingerprint for everything. We don't need to include the block body, right? We have a unique fingerprint. And so this single hash can represent uniquely a block and all the stuff inside of it. Okay. So what is inside the block header? Let's break down these individual pieces. So first we have the parent hash, right? The parent hash is just the link to the past block, right? So it's a blockchain. We have basically like a linked list. Every single block references the parent or the block before it, and you can then navigate down the whole list, right? Then you have the block number that just says what number of the height in the block, right? The blockchain. You have a state root. So this is using a Merkle root, and we'll talk about Merkle trees and Merkle roots very soon. But this represents basically a single hash that can succinctly represent all the data on the blockchain. So if you have your blockchain in a certain state, again, let's imagine that you and me are running two blockchains. I execute a block, you execute a block. It would be crazy that you and me have to share the entire blockchain state with each other to verify every account. We have to go like, hey, does Alice have this balance? Yes. Does Bob have this balance? Yes. Does Charlie? It wouldn't make sense. Instead, we can do some kind of clever hashing so that I have a single hash, you create a single hash, and if our two hashes match, then you know that we have exactly the same data, right? That not a single byte or a single bit could be different because of the property of hashes, right? So the state root represents that single representation of all the state. Then you have the extrinsics root. That again is similar, that we have this block body, we have a whole bunch of different extrinsics and transactions in it, right? And we can represent all of that into a single root. So I could be able to verify, is my transaction included in this block? I can actually use the root to make sure that, hey, I'm actually being included without actually having all the other extrinsics. And remember, extrinsics can be very big, right? So we talked about a code upgrade, right? A code upgrade, that extrinsic will include a new WASM runtime. That will be 2 to 5 megabytes, right? So it would be crazy for a light node, like your mobile phone, to be downloading 5 megabyte blobs all the time, right? So just a succinct hash will show that will represent all of the extrinsics in that thing without represent all the extrinsics in the block without having to actually have all the data, right? And the last piece here is the digest. And this is really kind of the most important thing for the light clients. And this is a bunch of like kind of auxiliary information allowing the light client to follow the consensus of the chain without having to actually execute all the consensus itself, right? Let's go into that a little bit more. The digest. Okay, so inside of the digest, there'll be a few different things. There'll be consensus logs. This is logs telling us about the block production of the blockchain, right? So it includes things like who is the block author and what slot are they able to build in. And all of you should have learned this, right, in the PBA X a little bit about the block production, right? The slots and all that kind of stuff. Then there's a seal. That's a signature from the block author proving that they actually made that block, right? Then there are the grandpa logs. Grandpa logs is all about finality, right? And grandpa logs will tell the light client kind of basically who the validator set is and when it will change, right? And this allows the light client, without having to run the whole blockchain, the whole state, keep up with who are the people I can trust, who are the validators actually putting their money on the line to give me information, to create new information, right? And this is how light clients are able to track the authority set, track the block builders without downloading the state. Let's keep going. So what is the light client's job? Their job is to verify the state of the blockchain with minimal resource usage, right? And the way they do this is with three things. They confirm finality, so they confirm which block is actually a finalized block of the canonical chain, right? They verify block authorship. They ensure that the block that they're receiving is actually authored by someone real and not just making up a bunch of stuff, right? Like imagine that I could just mint a block and just make fake proofs for everything else, right? I want to make sure that the author actually built this block. And it also follows the validator set. It tracks who are the block producers and who it expects to get blocks from. So let's go through these step by step. So confirming finality, right? So light clients will receive new blocks from a full node, right? It will be talking to it. But why should it trust that the block being given by the full node is actually accurate, right? Again, we work in a system where we assume there's no trust. We have to assume that two actors or any actor could be malicious, right? And I, as a light client, when I'm talking to some node, I need to be verifying that this stuff it's giving me is actually correct. Otherwise, I would just be talking to RPC, right? And this is actually a very common problem in the blockchain space. As you might know, extensions like MetaMask for a long time just talked to inferior RPCs, right? You had no evidence that the data it was giving you was actually correct. Now, of course, you know, there are other systems which kind of show that, like, hey, it's not really profitable for inferior to lie to the user or whatever. But again, these systems which are centrally controlled or that rely on trust can be attacked. Even though they're not being attacked today, they can be attacked tomorrow. You never know when these systems will break down, right? So what's important is that we need to be able to always, at any point in time, be able to know, can I verify this trustlessly? Can I, for myself, know that this information is accurate, not just trust the user giving it to me, right? So what the full node will do, in order to try to help the client trust it, is it will provide a grandpa justification, right? So grandpa justification is not part of the block. You won't go into the block in the header or anything and see the justification. This is additional messages gossiped over the peer-to-peer network, right? And this justification gossip basically includes information about validator set, as I said, and it happens in rounds. So basically, as nodes kind of have a bigger and bigger picture of the network, they will gossip what they know about it in the justifications that are assigned and give it to the client. And the client will be able to use information to confirm finality. We'll go into that a little bit more. But again, remember, one of the important things is when you think about these blockchain systems, you have nodes all around the world. Every node is going to have a different picture of what the blockchain looks like, right? There can be forks, there can be different blocks, there can be a lot of things. So it's important that these messages are being constantly sent to be updating the client, hey, this is the best information I know, right? So in the justification includes signatures from all the current block producers and validators. And these signatures are basically votes on what they believe the canonical chain is. This is what Grandpa is doing. So again, one of the interesting things about Grandpa, and we'll go over that probably later in Polkadot, is that instead of voting for just which blocks they think are correct, they vote for which chain of blocks they think are correct. So if we look at this image over here, we see that there are 3 forks of the blockchain, right? And we have different validators sign a message saying, hey, I believe that this chain of blocks is accurate. Now, in order for us to get finality, we need 2/3 plus 1. This is the Byzantine fault tolerance, right? Of votes to be able to show that we believe that this block will actually be finalized, right? If 2/3 plus 1 agree this is the final state, that will be part of the canonical chain, right? That is BFT. What we see here with 7 users is that they're all voting on different forks, but starting at this point, right? This chain and this chain, they both agree that this block is included. And this, I think, is like what, 1, 2, 3, 4, 5, 6 out of 7 people. This is enough to finalize that block, right? Even though we don't know about which one of these 2 is correct, because this is only 4, and 4 is not enough for 2/3 out of 7, right? We're able to say this one is correct because enough people voted on this chain, right, of blocks. And even though these guys up here are on a different fork, right? They don't even know the correct finalized block yet. It's fine because they voted on this chain. So they can all agree, at least at this point, that they're all accurate. And again, with peer-to-peer networking and consensus and all the kind of magic stuff that happens, really complex things, you're able to eventually, everyone eventually gets to the canonical chain. Everyone eventually gossips information they know and understands what is the most finalized spot. But remember, when you're a light client and you're talking, for example, to this node is telling you the last finalized block is this, even though it's actually this one, but this node doesn't know it yet, right? But what's very important is that your light client isn't being told that this is a finalized block, right? Because that would be bad. This is not actually finalized. And again, what it can do, the light client will receive these signatures, and the signature proof that this node up here can give to the light client can only justify that this block is finalized so far, right? And when this node updates and gets more information, then it will realize, oh, this block is also finalized. I'll join this chain and also update the light client. But again, the signatures from the validators prove, hey, do I have 2/3 plus 1 majority of signatures on a block hash? Then I can know this block is finalized. Let's pause on that real quick. Okay. These are pretty short, so we'll have time for questions too. But let's make sure you really absorb that information, right? So from the perspective of light clients, they are responsible for keeping track of the current validator set, and they are able to individually verify the signatures of each validator in that justification, right? I can verify the signatures. I see what they've signed. I can do it myself. So by matching the block hash with the signatures from validators, they are able to then trust all the content of the block header given to them by the full node. So again, remember, the block hash is the hash of the block header. If I can see a bunch of signatures on a block hash, which tell me that this is finalized, and then the full node gives me a block header, which matches that hash, I can trust all the content of that block header, right? And I use the word trust. There's no trust here. I can verify that this is all correct. There is no thing. So again, less trust, more truth, right? That I am able to independently verify with my own signature verification, with my own hashing, with my own block header data, that this is all accurate, right? It's impossible for a node to trick me in this situation, right? Without breaking like all of cryptography. Okay, second step. A light client will verify block authorship, right? So within the header itself are signatures and data from the block author who made the block, right? That's the seal, right? So inside the digest is the seal, and that's simply a signature of the block author for that block hash, right? There also is inside of there a secret VRF, which basically the author reveals to show, hey, I was the person allowed to make a block during the slot. So one of the things in Polkadot, again, you'll learn about this probably in more detail later, is that we don't want to expose who the block author will be for the next block. Why? Because what will happen is that you can attack that block author. Imagine if I know who the next person building a block is, it's way easier for me to attack the network. Instead of attacking all 100 nodes, I attack just this one node. And then I attack just the one node after it, and the one node after that. If I know who the block author will be, I could stall the chain much more easily than if I don't know. So one of the things that we focus on in Polkadot for resilience is hiding the fact that you will be the next block author until you make the block. And what we do for that is we use a VRF to basically have the block author reveal some secret number that everyone else can verify to show, hey, he is the block author, right? And then I can trust that that block is being made correctly. Like I can trust that this person was the correct block author. They signed this block. I can verify everything about the authorship of the block, right? I can trust that situation. So again, all of this again can be independently verified by the nodes on the network, including the light client, right? So less trust, more truth. Finally, the light client's job is also to follow the validator set, right? So one of the things we see in the grandpa justification, right, is that the light clients will see the current validator set, right? And again, the actual process of picking validators, etc., is a complex process. You might learn about the fragment elections and staking and stuff like that. All that is runtime logic, right? And that's a pretty heavy runtime logic. We cannot expect the light client to actually execute all of that code, right? It just doesn't make sense. So what we do is we include in the digest, along with everything else, any kind of upcoming changes to the validator set. So you can see here we have a schedule change and a force change signal that we can include in there, which will tell, which is the current authors telling all light clients, these are the new validators coming up in 10 blocks or 100 blocks, and the ones you should switch off to, right? So basically there'll be an election, there'll be a staking system, all the new validators are selected. The current authors, they will sign a message. I think I have this somewhere in the next one. Yeah, they will sign a message saying, hey, we are the current validators. You can trust us because we have a bunch of money staked, and if we lie to you, then we're gonna get all our money, like, you know, slashed. This is who the next validators will be, right? And then when for this block number, and when this block number comes, you should expect new signatures, right? But you know who they are. Again, we can even do the handoff trustlessly, right? And that's all happening again because of the information in the headers, because of the information in the digest, right? So it's really important what in this situation is that these validator changes are pre-announced, right? I can only trust the new validator set if it was signed by the old validator set, that they put their money on the line to tell me who the new validator set will be, right? And again, then there's a trustless handoff. I can always verify every step of the process. I'm not just given random new signatures and saying, hey, I think this is the new validator set. No, that I only trust new signatures from the list of people that were signed by the old signatures, right? And we can follow that process all the way back to the beginning of the chain, right? So with the announcement included in the digest and backed by the grandpa justification, light clients can always know who the active validators are, even as they change, right? Less trust, more truth. Every single part of this process is verifiable by the light client. So again, as you can see, light clients, they verify basically everything but the actual state transition function, right? They do not need to actually execute the code on chain. They just need to follow the headers, and they need to have enough information in the headers to be able to verify that every new block coming in is accurate and valid, right? And with information like the extrinsic root and the state root, then they can talk to a full node and get information from it trustlessly and verify on its own that the information it's getting is correct. So some other node is actually executing the code, right? It's getting the actual results. And I, as a light client, by following the headers correctly, can verify that the results it's giving me match what the headers tell me it should be, right? Yeah, and then the story begins. Okay, so this the scenario we're going to be going over, and we're going to be kind of walking through step by step, and touching on a bunch of different things, is the basic light client story. You have some kind of mobile phone. This mobile phone is connected to a regular full node. This full node is not an authoring node. It's just a normal full node, right? There's lots of those existing, and that full node, of course, is talking to an authoring node, which is actually building new blocks, right? And you can see there's information going back and forth between all these things, all trustlessly, all in verifiable ways, to create a full end-to-end interaction. And of course, we'll do something like a simple balance transfer from Alice to Bob. How does my mobile phone do a balance transfer without having to rely on RPCs that are not trusted? Wait, RPCs that require trust. So in a fully trustless way, talking to the network, actually verifying everything, actually using good light clients, right? And then one more thing I want to clarify. Okay, yeah. So here we have the light client app, right? What it does. We'll go over this in the presentation. So not too much here. The full node and the authoring node, right? And one thing I want to clarify is that I talk about light client kind of as a broad term. The Pappy guys kind of corrected me here. Inside of a light client application, like imagine a wallet app, there's actually two libraries, or like multiple libraries. You're going to be using some kind of like, mobile development framework that you want, right? You're going to be using a light client engine like Small Dots. That's the one actually doing all the kind of fancy crypto stuff. So it talks to the full node, it syncs the block headers, it verifies all justification stuff. And then you actually have something like Pappy, a Polkadot API, which actually is the one interpreting, is talking to the light client engine, getting raw bytes, processing the metadata, and getting for you the right types, the scale encoding, constructing transactions, etc. Right? So all of that kind of extra magic, the user friendliness, the things you've been learning about, is all coming from Pappy. But the light client engine is kind of more dumb. It's just not dumb, but like it's just focused on the kind of hardcore blockchain consensus stuff, right? That's the piece. But I kind of, for simplicity, I refer to the whole thing as a light client. Right? So you kind of have to figure out exactly where it works. But from my perspective, kind of as a blockchain developer, this whole thing is like this light client system. Okay. So let's start with any questions for this part so far. Yeah. Can we get a lot of hands? Yeah. Keep it up. Also, if your question doesn't get answered or gets to, you should put it in the chat, and I will look at the chat later. And also, you should write down your question so you don't forget.
Hello, it's Josefa here. So you mentioned like why we are running the line clients is because we need more truth than less trust. But in order to run the light clients, they are heavily dependent on the running the full nodes, like the one they has to get the information from the full nodes.
100%.
But doesn't it make like the point is invalid? Like you has these full nodes, which are the smaller numbers, or like they has to run full nodes, and then light clients, maybe we can run through mobiles and whatever. But then the proportion of light clients and full nodes, what's like how it's validate the point of it's not centralized and it's like more providing.
So Minja, do you agree that the interaction between light client and full node, from what I just went over, can be trustless? That there's no trust happening that the full node can lie to the light client, right?
But then a light client has to wait until the full node or the finality of the block has done. And then later on, it can verify, okay, this...
yeah, but block finalization is, everyone has to wait for block finalization, right?
But then what's the function of light clients if it has to fully depend on the full nodes? Like,
okay, so I have a mobile phone. I would like to use the blockchain. I would like to send you money. Should the requirement of the world we live in that my phone has to run the whole blockchain? No. So can I make a mobile app where I can do things like transfers, I can do things like know my balance, but I'm not required to use a full node? We can't change the fact that computer systems take energy. All I can do is I can create a system which, as best as possible, allows me to interact with the system with a small hardware without relying on trust. I can verify on my phone all of the proofs needed that if some full node tells me that I have this balance, I can prove I have that balance. I can know for certain that balance is correct.
No, but your initial point, when you mentioned the light clients, like it's less when we have like in most of the re-execution method, like all the clients has to run the full nodes and everything.
Okay.
And that makes the central like heavy computer and all that more centralized. But what's happening in this case as well, like the full nodes, maybe they can be centralized or the clustered because not everyone is running the full node.
So how decentralized your network is dependent on a lot of factors, right? If you require your network to run on full nodes, which are super powerful and super centralized, then your blockchain is centralized. If you, like in Polkadot, we expect nodes to run on basic gaming computer hardware. This is not cheap. It's like $5,000, but anyone can buy it from their store. Versus, again, like this, do the obvious example like Solana. As I understand, you need to spend like $30,000 a month to run like this intense thing. There's like 30 block producers in the world, versus Polkadot has like 300 or more, right?
So there is any proportionality of
Yeah.
it? Like how many the full nodes and light clients, for example, how do we verify that?
How do we? So okay, another thing that's important is that a block producing node is not required to be talking to a light client. A full node is. So even though there's 300 block producing nodes in Polkadot, there are thousands of full nodes. So let's do an example here. Let's go to telemetry. Let's look at this real quick. Hopefully the internet loads. But I think, again, what you're getting at is you're trying to somehow say like, how do we prevent centralization? Light clients don't solve decentralization.
Yeah.
Light clients allow a user without a full computer to access a decentralized network trustlessly. That's the thing. It's a set of tools that I can access this network trustlessly. Now, whether this network is decentralized is a set of things that the light client can't solve that. But at least I can access this network in a trustless way. So what I want to show in this picture is that you can see here there's lots of nodes all around the world, right? This is 1,844 full nodes around the world, right? Now, only a fraction of them are block producers. But even right now, I can show you a script. You can become a full node today running on your computer and contribute to the network, right? So, and what I'm trying to say is that if you could do that, and I use a mobile phone, and I happen to connect to your full node, I don't have to trust that you're a good guy or a bad guy. I can just simply interact with you, get proofs from you, and know whether or not you're giving me good information or not, or bad, through consensus proofs, through all of this verification. So again, I'm not making it so that you are good or bad. I'm not making it so that our network is decentralized. I'm just making it so that when I use my mobile phone, I don't have to run the whole blockchain to be able to at least verify the information is either correct or incorrect.
Okay, but then it's provide the scalability issue, because then again, as a light client, again, my question is depending on the full nodes, and maybe that proportion is very small, number of the full nodes.
How can you have a blockchain network where at some point you don't depend on somebody? Like there are 300, like you're dependent on computers somewhere, right?
Yeah.
But you agree, okay, so let's say without light clients. Let's say that I have a mobile phone, I'm talking to an RPC. I'm dependent on the RPC. But the difference is that I'm also dependent on a server somewhere, right? Mm. The difference is that when I talk to that server, it gives me some data, and I just have to say, okay, I believe you. In this case, with a light client, it's a set of protocols where I get the data from some server, and I'm able to verify every piece of it.
What if that block executors or the one, they are, the bad guys?
And I can verify. I'm sorry, I think you need to review cryptography, right? And the hashes. I can verify all the pieces. It's impossible for you to give me a malicious data if I follow the rules. I mean, that is, let me convince you as I show you all the steps of the light client. But if you don't understand this, I think that you need to review the properties of cryptography, right?
No, my question is just like the number of full nodes and the number of light clients. I can understand, like, what are you saying? Light clients give me access to access the network, but the full nodes and the block executors are the one who are, the light clients are depending on them.
Yes.
So what's the problem we are solving here?
That I can join the network with my mobile phone and verify the state of the blockchain.
And then what about the scalability of the blockchain? Because then blocks executors are maybe the minimum small numbers of people and one part of the world. That's what you mentioned about the other blockchains as well.
I think we need to move to another question, but I really don't agree with what you're kind of pointing at. But I just don't think what you're saying is accurate. But I'm happy to follow up in a chat. Okay, let's go next one. Sorry.
Oh, I'll go.
Yeah,
my name is Adrian. Yeah, so I was just wondering, what protocol are you using when you communicate between a light client and a full node? I'm guessing it's WebSockets or?
Yeah, I mean it's using the P2P layer. No, it's probably using the P2P.
P2P. Okay.
Yeah, if that's what WebSockets or whatever.
P2P.
Yeah, it's using libp2p.
Oh.
These things are also joining the network, as I
Got it.
understand.
Okay, and then I just have two more small ones. Is there like a registry for all full nodes that the light nodes know to scan and connect to? And then
Yeah,
what?
so this is the bootstrapping problem. What we have is in our chain spec, we have a list of boot nodes that you can connect to, and then you start connecting, then it gossips other nodes and you start connecting. This is not super great because the boot node list is kind of centralized. I think Jams has a solution where we're going to encode the boot nodes on the chain and update it. But practically speaking, that solution is we have a boot node, you know who to connect to first, and they will connect you to other nodes.
I see. Okay, and then there's a strategy to depend on, for determining which full node to connect to. Like I'm guessing that's just whatever's the lowest latency, or like how does a light client determine which full node to connect to?
That's a great question. I don't know exactly, but
Okay.
I assume you know exactly. Yeah.
So a couple of corrections, like
Sorry.
the light client. I mean, the light client that I know, which is small dot, uses many different transports. Uses WebRTC, although sadly Polkadot SDK still doesn't support it yet, but like it's compatible and it's been tested. It supports UDP, it supports WebSocket with and without SSL, because if you think about it, the light client doesn't need SSL because everything is trustless. So that was one thing. Another thing that Shawn said, it's true, but like it's also true that RFC8 has been implemented. So right now, once the light client is connected to the relay chain, it can use Scalamilia, like it uses this protocol for discovering like the boot nodes of all the parachains. So it's basically once you're in the relay chain, like now you have access to, like there's a way. There's a protocol for discoverability, peer-to-peer, to discover all the other ones, but the bootstrapping is still a problem. There is a proposed solution, actually, that it's very interesting, but hasn't been implemented, which is using like the torrent protocol, liter, for like basically you put the genesis hash of the chain, like in this case Polkadot, and then, because as we have explained many times, although some people don't seem to understand this, like even if a lot of bad actors registered in there, as long as you hit one good actor, that's going to give you access to all the other ones, and then you can block the bad ones. So like that's something that could be done. It's kind of using like the torrent protocol, where you put like the hash and then use the lists to discover. And I think, did I answer all your questions?
Yeah, I think so. Yeah, I think an important thing I'm learning from this is that it's a little bit agnostic as far as like the light client kind of adopts whatever transport protocol it seems to be. I mean, libp2p seems to be the popular one.
Sorry, then
Yeah.
there is a spec that is called libp2p, which is currently the one that it uses, and libp2p has a number of, IPFS also uses it, and it has a number of transports that are supported. Quick is going to be supported recently. It's going to be supported soon, although right now, like from web browsers, you still don't have web transport. Like, well, the new protocol is not available, which is like the quick one. But yeah, like you have a number of, and just for everyone to know, when you go to the PAPI DevTools, by default, it's using the light client on the background of your browser, which is freaking crazy how
See this? Light client.
performant it can be. So yeah, like sorry, that I'll shut up and I'll let.
No, that's
people
perfect.
talk.
Thank you. Yeah, appreciate it.
Hi, Krishna here. So on some time back, we mentioned that we also make a pre-announcement for next set of validators.
Yes.
So does that by any chance like reduce the attack surface for a malicious user to maybe attack that set of validators, or how do we?
So yeah, we can't prevent knowing who all the validators are. So again, I think you're talking about my comment. If there's 300 of them, I can't not know the 300. I have to know who the 300 are. What we can prevent is you don't know which of the 300 is the next one to attack. So in order for you to attack the network for the next block, you have to attack all 300 because there's like an equal chance that any of them could be the block producer, right? But you can't hide who they are in general, because it will be, I need to validate the signature and stuff. So but attacking 300 is a lot harder than attacking one, right?
So like the pre-announcement includes all the validators who
That will be selected for the next set. Yes, like all 300.
Okay.
One question related to the block, like kind of the client. I mean, is there any difference between the light clients that has a validator set for the validator and the light clients, which is normal user, I want to have my own light client and just for privacy, I want to no one to catch my RPC calls, stuff like this. Is there any difference in the block structure or the light node? I don't know how to say it, but the functionality that it has.
So sorry, there's two things. You said there's the light client for a validator and a light client for.
Is there any difference between them? If I
No, a light client is not a thing. It's an idea. A light client is the idea of this object, this program, which it talks to nodes and requests data and submits data, and the whole time can validate all the steps of the process.
Yeah, but what I understand about like having a validator, like I need to have the set of tools to validate, to participate.
To be a
in-
validator, you need to be a full node. You cannot be a light client, because if you're a validator, you need to execute the whole chain.
Uh-huh.
Yeah.
Thank you.
But one of the interesting things is like, in some ways, there are, I mean, some light clients, I mean, again, I don't want to generalize it because light client is just an idea, but in some ways, Polkadot has a light client of all the parachains. So what it does is the way but in this case, it actually does re-execute. It kind of basically, Polkadot re-executes the other chains, but only the block that it needs, and it kind of acts like, I mean, okay, well, I don't want to go too much into it, but in general, a validator needs to have a full computer. Like for mobile phone, you know, you're not be able to achieve those kinds of, you can't validate. Yeah, okay, sorry.
So
Yeah.
with light clients, because we talked about how with full nodes they need to know about runtime upgrades, and
Yes.
do light clients need to know about runtime upgrades?
So again, that light clients not actually re-execute the state transition function, right? So at that point, no point do they need to know that the runtime upgrade has actually occurred or anything like that. It just, again, will follow the header, follow the proofs, and then when it requests data, it will go.
So
Or maybe metadata though, right? Maybe metadata, it needs to know it's updated. But
yeah,
yeah, why don't you?
the reason is if you have communication with the full node and the full node doesn't respond to the runtime upgrade properly, doesn't the light client then basically be talking to someone who's like forked?
Yeah, but I mean, again, okay, there's so many things there. If one random node doesn't behave properly, you're talking about like a very specific, like any computer can have a bug. Like a ray of sun can flip a bit on your chip and
I mean,
cause a
like,
problem, right?
I guess I must like the light client isn't always talking to one full node; it's talking to
Yeah.
a range of them, and that's
And
why
if that
it
full
won't,
node
it won't
ends up
happen.
doing bad data,
Yeah.
the light client can connect to another node, right?
Okay. All right. That's
But-
what I was.
You have a comment?
So
Yeah.
just one thing. So the important thing about the light client, one of the things that one of the points that is being tried to convey here, and it's important, is that a light client absolutely doesn't need to apply the state transition function, right? It
Yeah.
doesn't need to like grab like all the bodies and like go one by one, click, and regenerate the state. It doesn't need to do that, but it is very convenient and it needs it for certain things to actually instantiate the WASM. So the light client, I guess you could have different kinds of light clients, but for the light client that we use, like you could have a super duper light client that actually doesn't even need to have the WASM instantiated. Someone could make that claim, and I don't disagree. But the light client that we use on a day-to-day, which is Small.dot, what it does is it instantiates the WASM. But remember the runtime APIs that we explained, it only uses the ones that are that it needs for like validating transactions, for getting the metadata. It's a runtime, right? But it doesn't just so that we're clear here. Does that make sense? So, and definitely needs to follow runtime upgrades because it needs to let us know, because like Papi needs to know. Yeah. It follows them because it needs to reinstantiate it. I hope that makes sense.
Let's do one more question and then we'll move on.
Yeah.
Anything else you can put in the chat?
Sorry, I got two small questions, if that's okay.
Okay, if you,
Um,
yeah.
Yeah, why do you need to keep track of the block number if you're keeping track of the parent hash?
I think that it's just in the digest. I don't know if it's actually relevant for consensus, but it's there.
Cool, thanks. And then the other one is like, how much more efficient, like on a benchmark level, is a light client compared to an actual node?
How much more efficient is a light client compared to a full node? Is that your question?
Yeah.
I think it's hard to compare, but I think if you would argue most of the work a blockchain does is executing the like transactions, and the light client doesn't do that. I don't think I can compare apples to apples on exactly how much more efficient it is, but like it's like a lot.
Cool. Yeah, thanks.
Yeah, like again, light clients run on my browser, light clients run on my phone. The minimum requirements to run a Polkadot node is like a gaming computer. So whatever the relative hardware impact there. All right.
I had one now.
All right, fine. One more, and then we'll go forward. Yeah.
So like without adopting data availability sampling, is there any way for the light clients to like verify the parachain's data availability?
So you're asking, is there any way for light clients to verify the state of the blockchain?
Like the data availability, like if without adopting the data availability sampling, the DAS,
Right.
so is there any way for the light clients to like verify the parachains, like, you know, the
So-
data availability?
So data availability sampling is only needed if you have a fragmented data storage, right? So in the case, we assume these full nodes, they all have the full current state of the blockchain. So it's not like you have to go to different guys. Like if you're talking to a full node, they have the full current state of the blockchain. Now, one thing that's important is that these light clients, I think it's designed right now, they don't talk to they can't go back in history, right? They only talk about the current state of the blockchain. So you don't need an archive node, you just need to talk to a full node who knows the current state. And again, you don't need data available sampling here because the full node has the full state. It needs the full state to be able to actually make the next block. So you don't need data available sampling in this situation. Okay, but anyway, we're about to talk about storage, so I think that's a great starting point. Okay, so let's keep going. So the next thing, so we gave you the high-level overview of what a light client generally does and how it can prove and follow the chain, and that doesn't require trust to interact with the full node. The next thing you need to understand is, okay, well, the light client is not only following the blockchain, but wants to interact with the blockchain, it needs to know things about the state. But we just told you the light client does not actually execute the state transition function. It does not do the thing which changes the state. So how can it know what the state is, right? For this, it will use Merkle proofs. And this next slides will show you the breakdown and composition of Merkle proofs and how they kind of work, and how, as a light client, I can actually get data from a full node and trust that that is correct. Okay? Let's go. So, Substrate uses a base 16 persistent Merkle tree. Try, right? And these are a lot of key terms. Hopefully you remember there's a repo that actually implements it. Oh my God, why is it broken? Nikos. Okay, let me. I probably have the local. I probably have the local host with pictures. I have pictures on my local host. So if you don't mind fixing whatever's on GitHub. Wait, is it showing on your computer? It's showing up because this is my local host. So maybe there's a file path problem. Okay, anyway, so we'll fix those pictures, okay? But here's the right thing. So as you know, a Merkle tree, right, is a way to represent a bunch of data concisely with a single hash, right? And it has additional properties we'll go over, right? But the general structure of the Merkle tree, how you build it, starting from the bottom here. First, you take all the data you want to store in your Merkle tree, individual data bytes, right? Then you hash it. All these white squares are hashes, right? Then you take any 2 or 16 or however many hashes you want, put them together into a new data blob. Then you hash that. Then you take 16 or 2 or however many more, again, hash that. Keep doing that over and over until you get to one final hash. And as we know, due to the property of hashes, if any single bit in any of these initial data changes, the entire Merkle tree, the entire root hash will change, because again, hashes are kind of, from any input will create a seemingly random output, right? From this, you get the structure where you have a single root hash, which represents the entire state of this bottom. And so again, if I have a blockchain, you have a blockchain, and we're both running the blocks, with this single root hash, you and me can verify quickly that all the data underneath it is the same, right? Now, on top of this basic Merkle tree, you can add this Patricia trie. This is basically an optimization. So in Merkle trees, because we have lots of hashes, and hashes are just kind of these random bytes, you get lots of overlap, right? Imagine a hash has 256 bits, right? That there'll be a lot of overlap in potential hashes. What we can actually do is optimize this in the storage, where we don't have breaks at every single individual bit, but we can actually clump up bits that are shared or bytes that are shared together, and then minimize the size of the tree, right? So in this case, I'm representing 6 words: parity, participate, party, process, procure, perspective. And if I did things naively, I would need a tree that has like at least 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 branches, whatever, right? But because there's overlap in letters, I can basically see P and RO is shared, and then spective is the only thing that's there, so I can put it all in one node, right? So basically, I can optimize the representation of this tree to basically minimize how many different nodes I'm creating, right? This minimizes the storage impact and makes the tree easier to navigate. So wherever there's shared letters, shared bytes, you will get a smaller tree. And then, of course, for most of the slides, we'll show you a binary tree, because that's easy to show. I mean, imagine making 16 lines for everything would be terrible. But everything we should talk about here scales to any size, right? So whether it be 2, 8, 16, 32, it's all the same idea, right? We use base 16. Actually, I mean, I'll be telling you this later too. We should be using a binary tree. Binary tree is actually better, but for a while we were using base 16 tree, and we still are. And base 16 is kind of nice because what happens is that every single branch is represented by a nibble, and a nibble is just one part of a byte, right? It's 1/2 of a byte. Okay. So anyway, so when we have a Merkle tree, we need to think about the complexity. What is the advantage, or what is coming from using this structure, right? So for this, we need to think about reading, writing, and proofs. So a Merkle tree read is bad. Instead of like for a normal like flat database where I would just read the item I want, in order to read data in a Merkle tree, it requires O log n reads. So this is slower, pretty significantly slower than a normal flat database. Writing is even worse. To write to the database, instead of just going to the point and writing the data, you need to actually write O log n reads, hashes, and writes, right? So I need to be able to first navigate down to my spot, write the new data, hash it, update this, hash it, update this, hash it, blah, blah, blah. So reading and writing in a Merkle tree is strictly inefficient. So why do we use it? Of course, it is great for proofs, right? If I were using a flat database and you and me want to verify the data that you and me have, we would have to share every single byte of that database. If you have a 4 terabyte blockchain, we would need to verify over networking all 4 terabytes are exactly the same. But instead, I can actually use a Merkle proof, or more specifically, if I want to get like one piece of data in that database, I would need to be able to not just get that one piece, but I need to also be able to get all the other pieces of it to be able to prove that that data is correct within the whole scope of the thing, right? You can imagine, let me give you one example here. Imagine instead of creating the Merkle tree structure, I just took all your data in the blockchain and put it into one giant hash function. Just one time, I just hashed it. I would still get a unique fingerprint for all the data, right? But for you to verify that hash, you would also need all the data again. What this Merkle tree structure has done, the tree structure, it says I'm able to create a proof for one piece of data without having to give you all of the data. I just give you enough data you need to get to this Merkle root. And this is where the efficiency comes in. So again, the entire design choice of creating a Merkle tree makes your blockchain slower. It makes it slower for reading, it makes it slower for writing, but it allows light clients. It allows trustless verification of storage in your blockchain. If you have a blockchain which doesn't have a Merkle tree, they're focused on number go up. They're not focused on the Web3 future. They're not focused on actually building resilient, decentralized systems, right? So this is what's better. And I want to go a little bit deeper into Merkle proof. So what makes Merkle proof so amazing is how little data you need to actually make a real proof, to verify the data exists. So in this picture, the only data you need to prove that this file exists are the things in the light blue. That's the only data you need. You can see this gray area, all these nodes, that's data that's in your blockchain storage. You do not need to send that information. And this is quite small here. A real blockchain would have tons and tons of data, millions of users. For you to get one user information, you only need these light teal nodes. And then the white nodes here is data that we can calculate. So you don't have to even send it to me. They're just hashes. So if you send me the teal nodes, I can hash this file, get this white node. You send me this data. I can hash these two together, get this white node. You sent me this data. I can hash, and I can calculate a big majority of it, right? And then the pink node at the end is the root hash, and this is known to all parties. So the light client knows the state root hash because it's in the block header, right? So I'm able to verify Shawn has balance 100, right, with just kind of 4 nodes here and knowing what the state root is. And it is impossible for a full node or for any other person to be able to create a set of hashes which exactly map to the same hash, right? Because again, hashes, they don't have pre-image attack, right? The hashes that are secure, you cannot control what the output will be, right? So you basically need to break cryptography in order to be able to create a hash where this structure makes sense with the data you want to input, right? So it's impossible for me to lie to you. Okay. And again, we've saved so much. All this data is not needed to be able to get the proof. Okay. So when we're going deeper into the Merkle tree structure, and I think it's good to know a little bit about the structure of the blockchain, of how we actually use our Merkle tree, there's kind of one main confusing part. There's 2 kinds of keys. There's a tri-key path, which is kind of tells you how to navigate down the Merkle tree, like where to bounce and where to go. And then there is this key value database key hash, which is like the actual hash where your data is stored on the actual hard disk. And we'll go more into that in the next slides, okay? So let's make this more clear. For that, I want to show you a very visual virtual example here of what it actually looks like. And I think Joseph has an even better visual example that he could show you later. But here's kind of the things you'll see. You'll see here. Ooh, what did I just do? I just killed my computer. Okay. No. Well, there's the part. Okay, yeah. So what are you going to see here? You're going to see here a key value database, right? This is like the actual database that's stored on your computer. Somewhere there is actual key value database. It has some hashes and it has some datas with the nodes on it. You will see different kinds of nodes with different prefixes, and they'll have different kinds of data in it. You will see the tree key path. This is like, the structure that you'll see to actually walk down the Merkle tree. So like when we talk about the Patricia trie, right? It has these like kind of shortcuts. You'll see here there's like a lot of shared keys and shared like A7, 7D. These are all shared. That's the path you walk down. And then there's actual node structure. Okay, so let's actually visualize this. Let's look at it one more time. So what do we see here? Here is a look at a piece of a Merkle tree. You have a, like a starting node, right? Starting node has children. It maps down. You can keep following the children to get all of the data. So here's 1, 2, 3, 4 pieces of data across these nodes. And you can walk down the path to figure it out, right? And you can see that each of these different values, these different data points, has their own tree key path, right? And you can see that some of these nodes, like for this one, it doesn't have any data. It's just a leaf, or it's just a branch node. These ones have values. This one has a branch and a value, right? So these are all the different kinds of nodes. So let's walk down the path. So first, okay, I'm trying to access, let's say, one of these final values. So first thing I do is that its value, let's say leaf 4, has the path A7, right? So I go to the node with A7, right? And the next thing after that is F. So then from there, I can find the path F, right? And then F will connect me down to the actual value, and I can get this number 4, right? So each one of these little lines here is a lookup into the actual underlying database, right? Let's say I want to keep going. Let's say I'm going to this leaf 3 now. Here from 7, I can go to D3, and then I can go look at the children, and then I can actually go 7. And one thing you can note here is that you can even have values here inside of a branching node. So one of the things we did inside of Substrate is we allowed for your Merkle tree to allow arbitrary keys and values. So any key that you could possibly imagine is allowed to have a value. And we allow this because we allow a node to have a value and to also branch to other keys, right? That's what allows for arbitrary key value choice. So you can see. So what you saw in this picture is that we had this kind of try path, right? So I go from A7 to 3, 3, 1 through 5, and I follow this path, and I just follow the nodes. It kind of tells me how to hopscotch down the information, right? And then each one of these lines was a look of the database, right? In the database, I have some node of information. I look up where the new one is. I go to that node. I look it up. Keep jumping around the database, right? And then you can see actually in the reverse way, when I want to actually follow up and create new nodes or update the path in the children, I'll take the hash of the node, and then that will be where I look it up. So let's see the next slide here, because I think that will simplify it. So the easiest thing to understand here is that when I set a tree, when you are designing your blockchain, you're putting things into the Merkle tree, you are determining what the tree key path is. You're determining what tree key you want to put the data underneath. But if I take the data that you want to put there and I hash it, I can then put that into the database, the normal key value database, under that hash and uniquely know its location. And then when I go and reference here, where can I find this data? I use that hash, and I know that the data which matches that hash will exist in that location. Does that make sense? Maybe say the sentence, and then we can ask any questions here. So given a value you want to store in the database, it will always have the same database key because the key is simply the hash of the data. If I want to store the number 5 or whatever inside of a node, I hash that like node 5. That gives me a hash, and I will store in the database under that hash that value, right? And whenever I go and look up in the Merkle tree, where do I go to find this value? I'll see that hash. I can go look it up, and I get that value that I'm looking for. Okay. Does this make sense? Kind of? Okay. I think it will make sense a lot more in the next picture. So what does this enable? This is a super powerful decision on how we can basically efficiently manage our database. So one of the things you might learn about is block pruning, right? So I have a blockchain. It has tons and tons of blocks. If you are an archive node, you store all of the block status, right? But if you're just a normal full node, you only need to store data about the blockchain up to the last finalized block, right? So what can happen is I'm running a blockchain. It hasn't been finalized yet, but I'm basically updating the state and importing new blocks. So here I have a block. This block in the block header has a state root hash, that R, and it points to all the data in the blockchain. Then a new block comes, and it changes. There's some kind of state transition, right? Let's say Alice transferred to Bob, and that changes the balance of Alice and Bob, which changes these hashes, which changes this hash, which changes this hash, which changes the root. But look, because Alice and Bob were the only ones who did a transfer, Charlie, Dave, Frankie, everyone else didn't have to update their stuff, right? So majority of the database actually stays unchanged. Only the nodes that need to be updated are updated. And again, we can use pointers to basically say, okay, well, this hash changed because this data changed, but actually a pointer to this data, which didn't change, can still exist, right? So I'm able to access all that, okay? And we can imagine again, another block happens, another data changed, right? And I'm able to again update the things and also keep behind the information which didn't change, which can still be pointed, right? And then eventually, as the old block gets pruned, I can remove data which is no longer relevant for the blocks that still exist, right? So in this case, this branch only lives in this block 42. And when I want to prune it, when I don't care about block 42 anymore, I can now get rid of that data from the blockchain and still maintain all the rest. And notice how all of these tree nodes in my database never got updated. They never were updated because they never changed, right? And it's because the value is just the hash. So if the value doesn't change, the hash doesn't change, I don't have to update anything. And again, the biggest key thing here is thinking about the tree path like a hopscotch, right? Like I started at the root tells me where to jump to next, right? So if I was using block 42, and this thing, starting at this root, it tells me, okay, I want to look up this data point, this 0 here. It says, okay, jump over to this 1, then jump over to this 1, then jump over to this 1, and jump to the 0, right? But if I start at block 43, it tells me actually jump over to this one. Even though this one still exists in the database, I already am on a different path because using hashes, I'm able to basically uniquely identify the path I'm walking down. So even though in block 42 and block 43, you can have the same tree key, like this 0 here, and this, well, okay, let me see. This 1 here and this 1 here have the same path. It has different data, and I'm able to access that different data because I'm able to start at a different route, which tells me a different path to walk down, right? Imagine, again, this is the beginning navigator. It tells me how to navigate everything. Okay, let's pause on this. Is there any questions about what I just said? Because this is kind of a pretty interesting and unique part of blockchain. Yeah, can we get a microphone up to the front? Sorry.
Hello, Martin here. So when we change the value,
yeah,
does it always go to the right of the tree, or it's because it changed its hash, so it changes its path?
There's two things. There's a tree path and there's a key value database hash. The key path for a certain value will always be the same. So like Shawn's balance, and you'll learn this again when we get to frame. Shawn's balance will always be under a certain key, or like the code is always under code, right? That's I think the best example. Is always under code. That key is always the same. Now the value under that key can change. When that value changes, the hash changes. So what you will know is that when you go to the root will say, oh, you're looking for code? Look at this hash. And on block 44, it'll say, oh, you're looking for code? Look at this hash instead. Both of these hashes will have two different WASMs stored in the thing, but they'll be different because they have different hash, right? And then your root will basically, the root hash will tell you how to navigate to the correct code, right? What's also important is that if you, between two blocks where the code didn't change, the hash doesn't change because the code is the same, right?
So the path didn't change
The
when.
path doesn't change. The code, like the code path doesn't change. But in the Merkle tree structure, which you're never exposed to, where in the database we look for that code will change. Because where we look at the database is the hash of the value.
Okay.
Here's another thing that blow your mind, okay? Imagine I store the same value in two places in the database. Let's say I have code and I have code old. And I put the same WASM blob in both. There are two key paths, but they'll point to the same hash. So I'll only have one entry in the database for both of those independent values because their hash will point to the same place.
But different paths.
But different paths.
Okay.
Exactly. And again, the path is just like the Merkle tree telling me, go here, go here, go here. And what it's actually doing in the database is like, go to this key, go to this key, go to this key, go to this key, go to this key. Two different paths could end up at the same final key, right? I keep thinking in my head, it's like a treasure hunt, right? You go to one tree, the tree says, go to this other tree. Go to the other tree, go to the other tree. Like you keep following it. You could end up with the same tree, even though the path you took to get there was different.
So just changing the value of a node, changing the hash, but doesn't change the path.
Doesn't change the path, exactly.
Okay.
Okay. Yeah, one more?
Yeah. So when you talked about the pruning, please help me understand. Like, so this is for full. So there are two types of full nodes: those who just hold the things that prune, but then there's valid, like.
Yeah, it's like a full node and an archive node.
So the archive node will not prune.
Yeah, archive node does not prune.
Okay.
Yeah.
That's what I mean.
But even like a full node, you can choose how much you want to store. So you can, in your node configuration, say, I want to prune 100 blocks. I want to prune 1,000 blocks. You know, like you can pick what you want.
Okay.
Yeah.
Is there a standard in Polkadot for how much they expect?
I think it's like, I don't know, it's a big number, but the rule in general is that you prune, you don't prune anything that's not finalized. Because if it's not finalized, it could be that you have a fork. So you might need to go back to block 42 to then go back onto the fork, right?
Okay.
So if you prune 42, then you have to re-execute everything. It'd be crazy, right? So instead, you wait till finalization. When finalization happens, then the data before it is not really super relevant.
So when a full node, like when you become a full node, you just have to take from the last point to finalize. Like
when you become a full node, you need to synchronize all the chain. But there are some tricks too. Like, okay, this is going deeper into stuff. Like, there are syncing tricks. We have this thing called like a fast sync or warp sync, which also does like what light clients do, which just follows the headers, right?
Okay.
And then imagine if you just follow the headers and then you get to the latest block, I can just download all the data from the full node with all the latest stuff.
Yeah.
But you know, the most standard way of doing a synchronization is just to re-execute everything.
Okay.
Okay.
I understand.
Let's do last question, then we'll keep moving forward, and then we'll ask more questions at the end. Okay. Yeah. Last question here.
Oh.
You have a mic or no? Yeah. Sure. Yeah. That's weird. Okay.
How do you keep track of the data you need to prune?
Yeah, that's a great question. I think they probably just use what is it called? Like the tracking flag, right? Like it's and there's a word. What's the word I'm looking for? Say it again, louder. Wait, there's a flag when it's like this data is being used, and then when it's 0, you can prune it. Ref count. They're probably using ref counters.
But isn't that kind of expensive to have to track down all the pieces of data?
Database Merkleized stuff. This is the most expensive part of the blockchain. Storage is the most expensive part of the blockchain. Like, if it could be done more magically, great. But like as a computer scientist, if you want to build a system which is like working, it's super expensive. Yeah, for sure.
Okay, this might be a stupid idea, but what if you just kept track of like all the accounts that you wanted to prune? Like as soon as you add a new piece of data, you know which data is also not going to be.
No, that's the thing though. So you and this is again no fault on you here, but I think you have a simplified version of a blockchain in your head. As a client, at any point in time, I could be tracking 4 different branches. Like, it's not that I know which is the canonical chain. It's not that there's only one truth. It's that there could be 4 blocks which are all different, which could all be the truth. And it's until finalization happens, I don't know which one is actually correct. So actually, I need to keep track of like all the different states. I can't just like, oh, change it and then delete the last one because it could have changed or it could have been a different fork. So I'm managing all these different states at once. And only when it's finalized can I kind of resolve the pruning. Assuming that there was ever one block, assuming there was never any forks, assuming that all that kind of stuff, maybe you could do what you're doing. But again, the client is actually managing like 4 histories at once. Make sense?
That makes sense. Yeah.
Yeah, and that's why there's rep counters. Like it could be that 4 different forks are depending on one node to exist. Then some of them move on, then 3, then 2, then 1, and then when it's 0, then we can actually remove it, right? Okay.
Yeah.
Let's keep going. I have time for more questions at the end, but like let's just keep moving and then we'll get questions. Only a few more slides. Okay. 4. Okay. So another interesting thing we can do inside of the Merkle tree is we can create this idea called the child tree, right? So basically the idea is that I have a Merkle tree, I follow the path, and at some point the data becomes a new Merkle tree, right? Now what's interesting about this specifically is that I could have a different structure inside of that Merkle tree. So I could have a base 16 Merkle tree, and then go to some path, and then starting at this point, it's a base 2 Merkle tree, right? And that base 2 Merkle tree will have its own root hash, will have its own structure, its own rules, etc. Right? So this is something that we've built into Substrate, but we don't actually really use it that much. I think it's only pretty much used inside of smart contracts, where basically, if you're building a smart contract system, your smart contract itself may want its own Merkle tree for its storage, right? So we give you your own Merkle tree within our Merkle tree, right? That's one of the ways you can do it. Okay, unbalanced tree. So we talked about the complexity of reading and writing data to the blockchain, right? And in general, one of the attacks you can do to a Merkle tree is by making it unbalanced. You can, for example, if you can skew the data so it's not even, like I showed you all these perfectly even trees, right? If you can skew so that all the data is in one place, then the average read and write to that location is going to be more than the read and write to other locations. But you can also use this as a tool to your advantage as a runtime developer. If I know, for example, some data, there'll be a lot of data for some things, for accounts. Like I know there'll be millions of accounts on my blockchain. But I don't want accessing the WASM code to be slow. I can inherently put the WASM code somewhere in the unbalanced part of the tree where I don't have to access it by going through a million accounts, right? So imagine this exact structure. Imagine that this is all the accounts on my blockchain. There's nothing I can do to avoid having a lot of accounts, right? Like if you want a lot of users, you're gonna need a lot of accounts. But if I know I'm gonna be accessing the code a lot of times, I could explicitly try to stick my information into a unbalanced part of the tree. So it only requires 2 reads to get to this code rather than 5, right? So again, if the users can manipulate your blockchain to make it unbalanced, that's bad. Because the malicious user will change the behavior for your not benefit, whatever the word is. But if I can adjust it and I know my blockchain, I can keep this even, but I can keep my important data separate. I can actually take advantage of the fact that my unbalanced tree gives me faster access to the data I use frequently, right? And so this is why things like the code path is actually, it's on its own. It's very easy to access the code and stuff like that, okay? Okay, there's also other problems. So we talked about proofs. All of this is building up towards light client proofs, right? So one of the things we need to do for light client proofs is we need to provide these data entry, right? This storage data. If the data I need to get the proof is really, really big, we then have a problem, right? Because my mobile phone can't download megabytes of data just to get a small proof, right? The whole point is that proofs are supposed to be small. So one of the rules we have in our Merkle tree is that if one of the nodes needed for a proof is large, we will just pop it off to a separate node and put the hash here. So if I know a node, for example, I think it's probably, if it's bigger than 256 bytes, we will just basically create a subnode which actually holds the real data, and the node that I care about will just be a hash. So that means that whenever I'm doing a proof of any data which isn't this big one, I will only ever need a hash representing that big node. Of course, if I'm trying to prove the big data, I need the big data. There's nothing I can do about that, right? But if I'm trying to prove this data, which is next to this big data, I want to avoid having this be my proof, so I just have a hash representing it, right? And so it's just a like optimization. And then there's also compact proofs. So compact proofs, basically, it does the best to only give you the data you need. So actually, what I showed you before is a compact proof. So a naive proof, let's go back to this. A naive proof would maybe give you all of these data points. A compact proof not only only gives you these ones, allowing you to hash the other stuff. So it doesn't give you the hashes. You can calculate that yourself. It may even optimize the structure within this data to make it smaller too. So we try to minimize as small as we can, give you the smallest proof needed. And again, all of this in mind about trying to support light clients, trying to support how can we give the minimal data needed for you to be able to verify all the information you're getting from the blockchain. And then automatically built into Substrate and Polkadot SDK is this proof recorder. So you don't have to do anything magic to create proofs. As your blockchain reads and writes data, it automatically keeps track of what would I need to give to the user to get a proof. So I can just call a good RPC, which we'll see later, like get proof for storage, right? I read some storage, and then the node will automatically generate a proof for the user. You don't have to do any work. We have everything in a proof recorder tracking those proofs and giving it to the users. Okay? Yeah, and one last thing to note is that there's a lot of trade-offs. When we're talking about proof sizes and making things good for light clients, there are trade-offs in what kind of Merkle tree you use. So a base 16 tree is good for disk storage and computation. There will be less nodes in a Merkle tree when you have 16 branches per node. There just will be less of them, right? Also, you'll do less hashing, right? This is all good for the full node. But for the light client, actually, when you use a binary tree, you will get less overall data because, again, each one of these points, I don't need 16 hashes, I only need 2 hashes, right? So it'll be a lot actually more data efficient for the light client to use this. And so actually one mistake that still exists in Polkadot today, which is being solved in Jam, is that realizing that binary trees are actually better for light clients. It's better for where the bottleneck is in our society. And the bottleneck in blockchain right now is networking speed. It's not computation. No one is complaining about how slow their computer hashes. They're complaining about the networking speed across a decentralized global network, right? So actually binary trees would be better and would be more efficient. And that's one of the things that we're solving in Jam. Okay, now any more questions? So again, let me recap real quick that what I've shown you here is now a way that if my blockchain uses a Merkle tree, and even though it's slower in reading and writing, I now have a super efficient way as a client to get storage proofs. And as we can probably guess, light clients will use this to their advantage so that they do not have to track all the state of the blockchain, but they can still understand or know the state of the blockchain whenever they want. Right? Okay, now questions. Whoever has the mic to talk.
Yeah, hi. Krishna here. So yeah. So my question was like when we prune and like keep just the latest the trees in cache, and that time is there a possibility of the shortest distance for a node being like increased, or does it like remain?
Yeah, it could. I mean, depending on like for example, imagine that I add a new key to my Merkle tree, which forces a new branch here. It could be that now my data is one more step farther away than before. That's normal. But again, on average, with a balanced tree, on average, it should be about the same, right?
Okay. Yeah.
Yeah.
Right. And yeah, just one more question. Yeah.
Of course.
Yeah. And we also mentioned that we can like utilize the unbalanced tree in our advantage. So would that would that be utilized when we like form the blocks, like possibly in, the collators would do that while like forming?
It wouldn't be collators. It would actually be you as a runtime developer. And we actually do this for you automatically. So when you build a palette with Frame, we construct the keys so that all of the data for each palette is consolidated within your palette. So if you have an NFT palette, an accounts palette, and a, I don't know, some NFT palette and accounts palette, how many NFTs you have will not affect how slow it is to reach your accounts. These will already branch them separately. And if you have a lot of NFTs, there's nothing you can do about that. It's just going to be slow, but at least it won't affect the account reads or vice versa, right? So those will already be fragmented into unbalanced trees. So you can think about it in your head. What we do is we create kind of unbalanced trees for each palette where you store the data separately. And we do that automatically. You just by using frame, you get this. And this is again one of those things that what I wanted to show you here is that this is not by chance, it's by design. We're actually making things efficient for you in many ways.
Yeah, I have one doubt. Yeah.
Please.
So, what kind of what type of Merkle do Polkadot involves? Like it's in the Patricia form, like in the compressed form, or like the sparse Merkle tree.
So your question is, what form is the Merkle
Yeah.
tree in?
Yeah.
Okay, so that's a hard question. Okay, so let's answer this. Your computer has a hard drive. In that hard drive is a bunch of bytes. That forms a simple key value database. Just a key and a value. No Merkle tree, nothing. That key value database is totally, you cannot understand what's going on there unless you know, okay, the key to reading this key value database is using a Merkle tree. Now the Merkle tree itself doesn't exist. It's not real. It is just a mathematical structure for how you navigate this database to get to the node you want. So when you read the database, there'll be like hash. Like in this database, majority of the items in this database will just be hashes, right? But then, for every hash, there'll be once in a while a big value in there. You won't know what that big value means until you start with the first root hash and then walk down the database and then get to the value, and okay, this is the value. But the representation of the actual Merkle trie is all virtual. The only real thing that exists is the key value database.
So the key is being decided by the hash of the value, right?
Yep.
Like the address of the
Yep.
for a particular pair, right?
Yep.
So what's in general the hash bit size, hash bit length?
256.
256.
So actually, wait, yeah, it's 56. Yeah, we use like 2256.
Okay, so the length for the Merkle tree is 256, right?
The length of the Merkle tree is 256. No. See, that's not right.
So the address for a particular value is being decided by the hash of the value, right? The key for the same.
So, let me say this. So, again, this is a very common confusion. So, we're talking about so there's two different keys. There's a hash key, like the key value database hash key, and then there's a tree key path. The possible number of possible hash keys is 2 to the 256, right? Every single possible combination of hash could be in the database as a key, right? Now, the length of the tree key can be infinite. I can jump around as many times as I want in this thing. There's no limit. It can be way more than 56.
No, so the address,
address.
So the address for a particular value is being decided by the hash of it, right?
Mhm.
So if it's 0101.
Sorry, does someone have a comment? But maybe that is actually use the whiteboard. Do we have that camera? Is that a thing that can do? You want to do it? I don't know enough for. Yeah, you want the web browser? Yeah. Yeah, but this is great. No, he has a great visualization. You want to plug in yours instead? I don't mind. You need to connect with the meet, right? Yeah. No. Yeah, microphone. Who has a microphone? We can get this guy. We remove the mic from your hand. Okay, great. But he has actually some really great visualizations here, which I think will unveil any mystery here.
Yeah, the visualization, I'll show it later when in the session. Now, because what she asked is a pretty good question. So if we
let's make it a little bit bigger. Is that okay?
Absolutely. So
is that better for everyone?
So can everyone see this key here?
It's big. It's super long, right?
This is super long. You know why it's super long? The way that this is generated is, roughly speaking, this system account, the system is hashed. Okay, account is hashed. It gets concatenated, and this means that if we look at a different account, we will notice that almost all system accounts start, well, not almost, all system accounts start with the same prefix, which is super, super long.
Yeah.
You understand why this is done is because what Shawn was explaining before, that we don't want to allow users, when they create data, to kind of be able to tamper with the height. And it's fine that it's super long because the try node, these nodes that that are explained, like as our Patricia, right? Like, so basically what it means is that like, if there is a common partial key, they just keep it there, right? And then, okay. So this is done. And then at the very end, there are some bytes that are basically like the public address of this account, okay? This is the case of this particular storage key, right? Now, this is the storage key. How, when the value of this storage key, and this is something I'm going to show later better in a visualization, so just like spoil, like, you know, stay tuned and stuff. But basically what's going to happen is what he was explaining, right? Like, in order to access the value, we'll have to walk down the trie, yeah? It will have to walk down the trie, and at the end, there's going to be a node that it's going to be called probably, most of the times is live with hash, right? Which allows us to have the actual value, because sometimes the values are very long, outside the trie actually, right? But anyways, like, sorry.
Yeah, I will also show, I don't need the microphone. I will show exactly the generation of this key in the part 3. And then when he was mentioning at the end is, I mean, there's 2 good things that he mentioned here. I want to reemphasize. Where am I at? That he was mentioning at the end, again, this leaf with hash solves this problem, the heavy node problem. So we can basically, you know, keep the data 1 leaf away, which is good for proofs. And the other thing they mentioned is, again, because we use a trie, because we're already optimizing these common phrases, it doesn't matter if there's big keys here. If this whole chunk is common across all the nodes, then it only counts as 1. It's basically just 1 hop, right? It doesn't matter that this is long. It's being long as a unique identifier. But because it's being long everywhere, it's just 1 hop. So it doesn't make your Merkle tree bigger. But this, again, this is certainly longer than 256 bytes. But yeah, like the key value database key can only be 256 bytes, right? Yeah. Okay.
I had a question.
Yeah.
So you were saying that the binary tree is more efficient, right? So why not use something like a Merkle mountain range? Is it because you want to like keep it unbalanced on purpose?
So Merkle mountain range, this is another structure, and I'm not sure if you learned about it or not, but this is not going to be useful for storage. Merkle mountain range is useful specifically for a kind of storage where I want to append data to it frequently. So how specifically it's used is the Merkle mountain range allows me to, every time the block creates a new block, I can append the hash to this structure. And the Merkle mountain range basically allows me to efficiently append 1 new hash every block. But the way that a normal blockchain database is updated is much more chaotic and whatever, and a Merkle mountain range structure is not optimized for that. That being said, the solution is simple. We should just use a binary tree instead of a base 16 tree. The reason we didn't do this was because when we started building Polkadot, so Ethereum used the base 16 tree. When we started building Polkadot, we just used the libraries that we already built for Ethereum, and it brought that along. But now we actually, when we're building Polkadot and actually focusing a lot more on like the light client pair chain validation stuff, we realize that proof size is much more important than the full node complexity. Yeah. Okay.
Yeah. Thank you. And another question. Sorry. So how do I know the computation required for me to like query or look up a hash before? So let's say I have a transfer.
Okay.
And I want to find out how long the execution time for this transfer is going to be. So how do I know this before actually executing the transfer?
Yeah, so this is called benchmarking. So we'll go over that if you're in the protocol track. We go over that. But basically, we have inside of Substrate, we have the framework for you to do benchmarking, which allows you to execute your extrinsics, determine how many storage reads, how many storage writes, all that kind of stuff, and actually know how long it takes to execute. And all this is turned into a weight. A weight is very similar to gas. And that weight is converted to a fee. So depending on how much the network is being used, you know, a transfer could cost more or less, but it will always cost the same proportional to another transaction, which has double the weight or half the weight or whatever, right? This is benchmarking.
Okay, but you'll need to find it. So before executing it, how do I know that it's going to be taking me a lot big time, like computation time? So whether I want to execute it or like.
So benchmarking happens as a pre-process. So when I launch, so unlike gas, so gas has a gas meter. So as it runs, it's calculating how much everything costs. What weights do, and we'll learn about this more again later, is that as a runtime developer, before I even do my upgrade, I calculate the weights. And then I know what the worst case scenario is. And then also we have this thing where we can do weight refund. Imagine you calculate a worst case scenario, but actually it's better. We can give some money back. But again, all this, I think you should save that for the frame stuff.
Thank you. Yeah, my question is regarding pruning.
Pruning, okay.
So for archival nodes, they don't run pruning, right? So is there a possibility, because our hashes are not completely collision free, they're just collision resistant, right? I mean,
yeah, but actually, it's intentionally, in this case, I think you're saying this, 2 data that's the same will go to the same hash, right?
Yeah.
That's perfect. I don't have to store it twice in the database. I just store it once in the database.
But is there a possibility for an archival node to, let's say, like, you've updated the data, but because they're not exactly collision free, like you actually have the same hash, but you don't know which version it is, right?
No, it doesn't matter. If Alice, imagine this. Let's say Alice and Bob can both upload to the blockchain their favorite song. Okay? If they have the same favorite song, I only need to store that once in the database, and both point to that. Right? Now, if I update for Alice and don't update for Bob, of course, I won't update that thing. I'll make a new node, and then Bob's will still be pointed to the old one, and Alice will be pointed to the new one. But
no,
I can optimize the storage.
yeah, so what I'm saying is, let's say song 1 and song 2 both get the same hash because they're not completely collision
No,
free.
but song 1, song 2 can't get the same hash unless they're exactly the same. That's what hashes are, right?
I mean,
what do you mean? Like a single bit different in a hash.
I mean,
create a new hash.
They're collision resistant, but they're not collision free, right?
A cryptographic hash function is beyond the ability of like supercomputers, collision resistant.
True, but like I'm just saying, like for an archival node, like, if you want like perfect history, maybe like
it's really not possible. I mean, I understand what you're saying. It's really not possible. Again, if you had full access to put any kind of bytes on the blockchain, you could perhaps do a collision. By the way, we use Blake 2. Blake 2 is like, I don't know if there's any known collisions. Like if you used, there's like a bunch of old collision shitty hashes, which are bad. But like Blake 2, I don't think has any collisions that we know of. But if you could control every single byte, maybe you could find one collision. Maybe if you would use all the power. But even then, does your blockchain state transition function allow you to put exactly the bytes you want? Because even your bytes, even if you had exact control, you don't have control over like the structure of the node, right? So like there are other layers of data being attached to your data, which you don't have control over, right? So it's pretty much impossible. But I understand what you're saying is if hashes failed. By the way, if hashes failed in the way you described, we have much bigger problems. Hashes are used in signature writing, right? So you have a much bigger issue. Like Bitcoin would be compromised, right? Like that kind of stuff. Another comment by Justin?
If you go to the Puppy Dev tools and you check, and you can see the hashes that are being used for generating the keys for the values that the user enter, which is what we cannot control. All the keys, or practically speaking, all the keys that could generate an hypothetical, super hypothetical hash, they have a concat. They have a concat. So the concat will prevent it. It's a Blake 256 concat. So if it's 2 different ones that happen to have the same hash, no problem, because the concat will prevent it, actually. Yeah.
Can I ask my question?
Yeah. Go.
Oh, hi, it's Ben. I just wanted to ask, within the ecosystem, is there any discussion about introducing Verkle trees as opposed to Merkle trees?
Yeah. I don't know about Verkle. I know that Vitalik wrote a blog post about Verkle trees, and I don't know enough about them. What I care about more is the properties of the thing. So if Verkle trees support light client proofs, sounds great. I don't know what the advantages are. But I'd be happy to look it up and maybe make a comment after lunch. Like, I would look it up. I don't know. Okay. Microphone, Mike. Yep. Okay. Sounds good. Thanks. Yeah, comment?
What kind of structure are tri-keys stored in?
What kind of structure is a tri-key stored? So tri-keys are not actually stored anywhere. They are generated using things like PAPI from the metadata. So the metadata gives us the information we need to construct the tri-key. So again, the perfect example, and we'll go over this in section 3. I think I have this somewhere. So this is a kind of like a thing, but the key will be the hash of the palette name, the hash of the storage name, and then the hash of the key you want us to do. So here, the hash of the word system, the hash of the word account, and then the encoded bytes, and then the hash of that encoded bytes of the account. And so in this case, the string system and the string account comes from the metadata, and then basically Papi knows this is the way Frame generates keys. So it's not stored anywhere. It's like generated on demand. I guess they probably could do some pre-hashing and store it like for caching, but like practically speaking, it's all dynamic. So if you make a palette called, my super cool palette, it will follow these rules. But anyway, this is the next slide, so I'm skipping ahead. Another question? Another comment? Okay. Can I get started? Okay, I should get started because we have time before lunch. They can't go to lunch early, right? I mean, I know, but then it's just like we're gonna lose 20 minutes. Let me see. What am I doing? Yeah. Okay. Well, let's just go into. Yeah. Let's start this, and then I think I'll stop at a point where it just kind of touches on metadata. Okay. So this is the next presentation, part 3. All right. So now we've done it. What have we done? We've proven to you that a light client can follow the blockchain. We've proven to you a structure for light clients to be able to read data trustlessly, right? So let's actually start and create a transaction. Let's actually start to read data and transact on the blockchain, okay? So the first thing the light client will need to do is fetch the up-to-date metadata, right? Because it's not going to know how to interact with the chain. It's not going to know what's going on in that blockchain, right? So remember that in the Polkadot ecosystem, all blockchains can constantly upgrade and update their state transition function, right? And can change the functionality of their chain at any point in time, right? So it's important for the light client to be able to, what is the up-to-date version of the APIs I want to call, the storage, everything, right? Now, where does the metadata come from? The metadata comes from the runtime. So the state transition function code, inside of that blob, there's an API called get metadata. And I can call that, and I will get that metadata structure, right? Which you've seen and we've been talking about for a while now, right? And this will tell you everything you need to know about the runtime at that point in time, right? So it'll tell you all of the all the palettes that are there, all the functions that are there, all the functions, what parameters are there, what types those parameters expect, and all the type structures, etc. We'll show you constants. We'll show you a bunch of other things I'll talk about later. But it shows you everything you need to know. Now it's important again that this metadata comes from the runtime code. So imagine you have the history of your blockchain. It's millions of blocks long, and there were hundreds of upgrades. If I want to be able to read or understand the blockchain at some point in time, I need to look at the runtime at that point in time, which is in the state. I get the metadata for that point in time, and I can then talk to that blockchain at that point in time, right? Now again, the light client is always talking to the latest version of the blockchain. So it's always getting the latest runtime and the latest metadata. But again, the point that the metadata and the runtime are kind of connected together is important because it's always about the metadata for that chain at that time for that runtime. Okay? So, and we were talking about this, the frame has a metadata format. So again, metadata is kind of a more broad idea, but frame imposes kind of our way of doing metadata. Like this is like when you use our framework, you get it. So you can build a blockchain using Substrate that doesn't use metadata if you didn't use our frame libraries, right? That blockchain would work. You would have a blockchain to build blocks. When you go to Papi and load your blockchain, it would not know what to do because all of our ecosystem uses this standard as like the standard. But technically speaking, you could build a blockchain without frame, without metadata. It would just be really bad, right? Now the better question to ask me is, can I build a blockchain without frame but still has metadata? The answer is probably yes, but man, you'd be like, rebuilding a lot of the stuff that we want to build for you anyway, right? I think it would not be the smart thing to do. And then we already showed you that, in Papi, you can get the metadata JSON, you can see the structure, you can see all that kind of stuff. And then there's a repo, frame-metadata, which shows you a lot of how that code is being generated, if you want to go into it. Okay. So let's actually go here. So let's say that I'm a light client, and I want to get my current balance. How would I do that? Now, obviously, programmatically, it's a lot different than me as a human going and reading stuff, but we are humans, let's actually go and read stuff. So I know that there's going to be a palette called system. I know that system is going to have in it a storage called account. And then this account has some value there, a key and a value. right? The key is type 0, the value is type 3. So let's go back into here. So there's a storage system account where I give it a key of type 0, I get a value of type 3. So let's look at that. So let's look at the lookup. A key of type 0 is the account ID 32, which happens to be a 32 bytes of a U8. So this is the public key, right? So if I take this storage and I give it U832, right? I will be able to get some value. And if I go to ID 3, what I'll get back from that is an account info, right? I'll get back an account info. And the account info has multiple pieces of information. It has a nonce, it has consumers, providers, sufficients, and then data. So you notice all of these are the same. Nonce, consumer, providers, they're all U32, right? So some number tracking, right? And then data is a big type. It is a type account data. And account data has free balance, reserve balance, frozen balance, and flags. And you can see that free balance, reserve balance, and frozen balance are all type U128, right? Balances are big. So you can see here, just using the metadata, I'm able to identify there's a storage that I can query, the types that I expect, the input it wants me to give, and the output it will give me, right? All of that, right? So that's what this is. So I type 0, and it has a storage with prefix system, storage with prefix account. And by the way, I think some of those things are also in there. So let's go back to the JSON real quick. If I go to this, yeah, the name. So see the system has a prefix system. So it could, I mean, again, the way the frame works, the name and the prefix is almost always the same. But this prefix is what is actually being used as the thing that we hash to determine the key, right? All that kind of stuff. So there's actually something called tagged prefix. Okay. So this tells us everything we need to know to query the blockchain. So let's go. So I showed you here the key type lookup, right? The U832. I want to show you here, this is just a small FYI, the Alice address. So you might have heard about the addresses Alice, Bob, Charlie, etc. These are actually like developer accounts. So there's this well-known seed. This is like a normal seed phrase. You shouldn't use it because it's very public. And if you take the seed and append to it the hard key Alice, you get the Alice account. And same with Bob, Charlie, whatever. So if you want to, and what I do actually, in my Polkadot.js, I actually store Alice and Bob. They're one of my accounts, right? And I can go and play with them directly from Polkadot.js, whatever, right? So that's just how they're generated. But you can see here then, if I want to read that storage I just described, this is the process I'll do. So I know, because of frame, that the storage is the hash of the palette prefix, the hash of the storage prefix, and then the hash of the encoded key, right? And we saw that the prefix is system, so the hash of that is this. So I can actually show you, so I have this util. This is in the useful links. There's a forum on the Discord, useful links, and I have basically a bunch of hashers here. So if I do Blake to a string, I do system, but not Blake to. I need to do XX hash a string, so I'm doing a weaker hash, system. I get 26AA, right? And if I look here, 26AA. And if I look here in the console that Joseph was showing us, if I do storage, system account, where can I see the? Oh, I'll just create here. Look at that. So but Alice, look at this, 26AA. It's right there. So this is, so again, everything is, it's not magic. Everything's happening. All I'm doing is taking the word system and taking the hash. Like you can calculate it as many ways as you want, right? So this is that hash, right? And if I do the other one, account, capital A, account, B99D. I'm gonna find that in the Poppy, right? I'm gonna go here, somewhere, blah, 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 B99D. So now I know this is the end of that first system hash. This is the beginning of the account hash, right? And then at some point, let's see where the end of this, it ends with 1DA9. Where's 1DA9? 1DA9. That means I know that this is the beginning of the account hash, right? So let's go back here. For the hasher, for accounts, we can actually go back. We need to go look at this metadata. There's more information in the metadata for us that we have to explore. Let me go back here, blah, blah. This is the JSON. Okay, I'm going to, nope, I want to refresh this so it hides all the, okay. System account, look at this. It tells me which hasher I should use. So even different storages could use different hashers depending on your needs. So in this case, I could choose to use Blake 2, which is a secure hashing algorithm, or for other ones, I could use like 2x, which is like here, 2x, which is a non-secure. And again, we'll go more into storage, in the runtime, why you would use different ones, but you can see the metadata is telling us which hasher to even use. So here, to get the system account, I take the user's address, and I have to Blake 2 128 concat it. So it's a special kind of hasher. I will actually go ahead and do that for this, and you get this result. Now, Blake 2 128 concat, what it does is it takes a hash and then concatenates the actual storage after. So if the user's address is D439, D43593, you'll see I find D43593 here. So this part is a unique hash, and this part is the key that we hash to begin with. And the reason we do this is that if we just hash the key, we lose the information about what the key was. If we hash the key and then concatenate the key on the next beside it, I basically create a transparent hasher. I can tell the user how to go backwards, right? I can tell a DApp or a light client that this was the account matching this key, right? Something like that, right? And I can also do things like iterate. I can iterate over all the accounts in the blockchain, knowing all their keys. Otherwise, I would have to have a hash table lookup, right? That would be crazy. So we use the transparent hashing tool. And when we combine and concatenate all of these different bytes, we get this final key here. Now I take this final key, and I go to Poppy, and I search it. Oh, let's turn this off, and I decode value, enter hex. You can see here I get a balance, right? And so I'm able to independently construct this key. Again, the light client is doing the same thing, but obviously behind all the Pappy libraries. So Pappy in the background is taking the metadata, is doing all the stuff and determining, okay, well, your account will be under this key. I generate it for you automatically, and I query that, that storage. Maybe a little more time. So what you can do then is when you want to query the value from the full node, you can call the state get storage RPC directly, right? So I'm showing you here this, this palette storage stuff, but I could actually take this exact key. Instead, I can go to the RPC calls. I can select the state get storage RPC. This is like, like in low level, and I can call it. I need to put this in quotes, I think. Null. Is it the wrong? It's not a. It's an array. Of the state? Wrap it into another array. Okay, wrap it into another array. Oh? I need two parameters, right? I need the state. Let's go explore. I swear to God, this worked. Oh, I gave you feedback on this one though. This is state get storage. Is that not fair? State get storage. No, I just want to get storage. I want to do it with the key. So it could be that this account has no value. Yeah, let's do it again. So let's do this. Let's get this thing. Let's get Alice. Well, Alice probably has no storage though. That's the thing. Okay, she has something here. So let's get this key. Sorry, maybe it could be that my own slides have a bad key. If I go to state RPC calls, state get storage. I do this one. Yeah, okay, it's okay. So it could be. So I need to update my slides. Someone messaged me to update my slides with a better hash. But here I get a bunch of bytes back, right? Now again, we don't know what these bytes mean. These bytes could be anything, right? Only if I know what value I expect to get back and how to decode that using scale will I actually be able to understand what this value is, right? So again, going back to what we learned, going to the metadata, right? That when I call the system account, I'm going to get back a value of type 3, right? And value type 3 we saw was that the nonce and all that kind of stuff, etc. And we can decode that, right? So this is where scale is coming in. This is where, when I actually do the raw calls, like, it's talking RPC, I'm sending bytes, it's giving me back bytes. I have no idea how the bytes work, right? But again, all of this metadata stuff is actually creating the key that I can call, and the value I get back, right? Now, one thing is the problem here. I went and I called get storage on some key, and it gave me a value. Should I trust that value? No, this value is not a proof. This is just a value. This is just telling me something. There's actually a better API to call, which is what this next slide is. The better API to call is state get read proof, right? And you can see get read proof gives me a lot more data back, right? So let's do that real quick. So let's do the exact same key. Let's do the exact same key and do state get read proof. And I need to include to the read proof, I need to also include the block hash, right? So I include this block hash. Ugh. So you need you need an array in here. Bro, this worked the other day, actually. This one? It's in the clipboard. Remove it. Second argument, okay. This, like this? Or is it in the array? Let's try it. Try it, put it in the array. Okay, array of proofs. Sorry, buddy. Here. You know what I'm gonna do, buddy? Dude, I'm sorry. This is sorry for the Pappy guys. They're doing really good shit, by the way. They're really good work. But Polkadot.js makes this a little bit easier, to be honest. Let's go to Polkadot real quick. Blah, 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 blah. Let's go to RPC calls. Let's go to state. Let's go to get read proof, right? Here's the key. Wait, the key I want. So going back here. Where's my storage key? That key was bad, right? This key is good. This storage key. Wait, child storage key. No, storage key. Wait, this is actually not good either. What is this child storage key? Get read proof. Okay, get read proof. Sorry, there's no child storage. All right, I get this storage, and it will get me the latest block hash. And you can see here, I get this. Wait, sorry, guys. Come back. We're almost done. I get this larger proof. So this is telling me at some block hash, right? And block hash is unique. Here is a read proof of this data, right? And then I can actually go and actually verify that this is actually the information needed to construct that Merkle tree to actually get that proof. And so we actually go into here. Let's go back to my slides real quick. The data, when I query, is 623001, right? When I get the read proof, you'll notice, look at this right here, 623001. My data is in the read proof. And as we went over already that, you need the data as part of the proof, but you can see my data is actually in there, but it's surrounded by a bunch of other hashes and a bunch of other information needed to construct back to my state root, right? And so somewhere here it'll construct it. And so I have here in the link in the slides, a Rust project, which takes exactly this data that I put into my slides, and it uses our libraries to call this function here, the read proof check. And if I run this, you can actually see that the proof is validated, right? So you can actually do all the steps I just did, take a state root, take a storage key, take a value, call the read proof, put all that into this file with your own stuff, and then run the program, and you'll see that it will actually verify the proof. You can try to change any byte, change anything you want, it will not verify the proof, right? So here's a full end-to-end storage query with a real validated proof that a light client can actually use, right? I can actually validate that this data is on chain, right? Because I have the block header has the state root matches this storage proof. Okay? And the last piece I want to go over before we go to lunch is then, of course, this data is just bytes. So we actually look up the structure. We saw that it was nonces were U64, some U128s, and we can get a final structure like this, right? So when you actually run your DApp or you actually run your light client or whatever, you actually have this information. You have like a nonce field, you have a sufficiency field, you have a free balance, you have a reserve balance, and you can access and use all those types normal, right? From all those bytes, from all those types, through the metadata, you get normal usable items. Okay, so let's stop there for before lunch. And is there any questions? We have 5 minutes. Yeah, can we get the mic to those raised hands?
Hi, how do we avoid that confusion that just happened? Like, how do I know what input to actually, how to format my input?
Right. So this, I mean, that's again, humans shouldn't be doing what I'm doing. This is all programmatic, right? Like, a human doesn't go and type in an RPC call with like quotes and stuff like that.
Yeah.
So if you use the right libraries, like Poppy, it'll just handle it for you. My suggestion to them was to make some of these, instead of making it just empty arrays, like give some fields that are expected. But I think they don't do that because right now our metadata doesn't like define the parameters of the RPCs, right?
So let's say,
Anyway, wait, the thing is, humans don't do what I'm doing,
Yeah.
right? I'm acting like a light client, and I'm showing you that thing. But basically, you know, the libraries handle it for you.
so let's say for now, I would look at the Polkadot SDK or whatever and see the type signature and then format my input for that, just for the sake of getting that.
Okay, let me make sure that we're fully clarified here. So actually, let me make it super simple. If I'm building a light client mobile app, I won't have to do any of what I said. What I'll do is I'll do something like import, you know, like Poppy or whatever, I don't know. And then I would do like, you know, like let, I mean, by the way, this is not correct, but let's take let API equal Poppy dot API dot initiate. I don't know. I'm just making up shit. And then at some point it'll be like API dot storage dot query dot balances dot account, and then it'll be like address. And this function will be generated for you automatically, and will do everything I just did there. Like it knows that when I call this, it's balances, or like, you know, this is system, sorry, system. This will automatically know what key to generate. It will automatically know what hasher to use, and will automatically give you back let my number. This will be a type, you know, U128, or like, or you know, whatever, the account data. It will return that automatically. So all that, like, again, libraries handle all this for you automatically. What I want to show you here is like a little bit behind the covers, so you know that like it's not just doing it without trust. Like there are ways to do this all trustlessly. We can actually verify all the information and get all this stuff, right? All the way from the metadata, all the way to the storage itself. But this is what's actually happening inside of inside the libraries. Yeah. Okay. Other questions?
Yeah, hi Krishna this side. So we saw like we received proofs as well. So were those proofs by any chance like the hops that we make to get the exact data?
Yeah, I mean, so this array of hashes exactly should be these light blue squares. It's like exactly. Like it's not even like kind of. It is exactly those light blue squares. And if you knew the exact structure of the Merkle tree, you could write this code yourself. And I think that Joseph will show this later, that he actually built something like this. But it is like is no mistake how many even data points are here. Like this already tells you the size, the length of the Merkle tree and stuff like that. It shows everything. It is exactly one-to-one with this proof.
Okay, yeah, got it.
Yeah.
Thank
I mean,
you.
it's pretty cool.
I guess I'm wondering, so at which point in this process did you figure out what the steps were to get to the data that you were looking at?
So okay, that's a good question. So at some point, I showed you how to make the key. I sent the key to RPC, and your question was, how did I get the database entry?
Yeah.
So the client is the one who will do that. The client built into it is a library. Like I have Substrate running on my computer. It's a program. In that program, it uses the library, which is the Merkle tree library. And the Merkle tree library is the one that's like, oh, give me this key. I'm going to hop, right, in the database and find the key. So there's a library in between that you never, as a developer, really touch.
Yeah, I guess maybe I'm missing some part of it, but like, so I saw the two prefixes that you used. That makes sense.
Yep.
But like after that, like, so I guess like the hash, does any part of that become the Merkle tree path?
All that whole thing was the Merkle tree path. So that
Ah.
system hash, account hash, and the whole user's address hash is all the tree path.
Okay, so that must mean like if each hash can like like maybe deterministically goes to a different Merkle tree path. Maybe it doesn't. Maybe it like allocates a new one. The
Yeah,
client.
exactly. So every single account will have a unique last part of the hash. Like all the accounts have the same first two parts. They'll have a different last part, and that will basically put us into a new place. So again, if you imagine, so this is the first node is system, the hash, and then there's only one. This is balances or like account, the hash. When I add the first account, it will be here, right? The hash of address 1. As I add the second account, it will make hash address 2. And it could be, address 3, right? And it could even be like address 3. It could even, depending on exactly the hash thing, it could be at some point we actually make a branch node here. So this is branch. And now this is where we put address 4, right? Like, again, it depends on how the hashes look like. But like, you just keep adding accounts to this thing, and it will just keep following the rules and branch everything. And then again, because of the way we did it, the key path uses the address, the hash of the address to determine the key thing. No two addresses will have the same path, right? Because every address is unique.
Yeah, I guess what kind of makes me nervous is that if there is like a one-to-one mapping, like I guess there's two ways I can see it. Like the node, like since each node technically should have the same state, the next time they get a new address, they can like figure out, okay, we're going to insert it exactly at this level, right next to this existing node. But if there is like some deterministic function to generate some path from the address that you provided, then I feel like there's going to be lots of nodes without any nodes next to them.
There's going to be lots of nodes without any nodes. That's okay, because the Patricia try optimizes whenever there's like empty nodes or whatever, like it just consolidates it all into one, right? So it's not like I'm doing like a bunch of small squares to get to my thing. If this is one giant chunk and it's the only one that exists, that all becomes consolidated into one Patricia try. So the try part of the Merkle try is what makes no matter what data is in the Merkle tree, the most optimized compact version of it possible.
Okay, yeah, that makes sense. Thanks.
Okay. It's really maybe my proxy. Yeah, there you go. Anyway, so no questions. Okay, so let's get started. Once I get this screen sharing. And then share screen, allow, entire screen. But who can see my screen? We can see my screen, yep. Okay, let's keep going. So what did we just last do? We went through all of the steps to read storage from a blockchain, a full node, right? So a light client actually went and made all the steps, RPC calls, serialization, metadata, etc., to actually read data from the full node, but do so trustlessly, do so with a read proof, right? And from that, we were able to see the balance. So again, the scenario we're trying to do is Alice is going to do a simple balance transfer to Bob. She might want to know what her balance is before she does the transfer, right? So a basic query like this will tell her, okay, she has a balance of whatever this number is, right? Now we actually want to go and construct the transfer extrinsic, okay? Let's take a look at that. Okay, so the full extrinsic payload is a bunch of bytes again, right? And it contains a lot of information. So you'll have inside there a prefix, which is the extrinsic version. This thing called the preamble, which is like the address of the caller, the signature, and then any signed extensions. We'll talk about that in a second. And then, of course, the function call. What function does this person actually want to call, right? And you can find this exact same structure if you go to the unchecked extrinsic. So if I go to, so actually, by the way, a few things. One plugin I really love in VS Code is the Peacock plugin, I think is what's called. It's called Peacock, I think, right? It gives me this color. So I can really easily, like, okay, this is purple is the Blockchain Academy. This pink is Polkadot SDK. So I can do it through. I recommend it. It's very nice, especially if multiple Polkadot SDK things open, you can switch between. I always, personally, love having Polkadot SDK open. There's no, like, we always talk about less trust, more truth. There's no further truth than the SDK, than the code itself, right? So when I talk about, teaching you these ideas, there's a pub struct unchecked extrinsic, and this is where I'm going to be able to see the preamble, the function call, right? I'm going to see all the things about this. So you can actually see what I'm talking about existing in real life, right? And look at this, the preamble, it has an address, signature, extension, right? Look what I have in my slides. Address, signature, extension. This is where it's all coming from. I'm telling you from the truth, but you should not believe me. You should also verify with the code, right? But yeah, so there's that. So let's take all these pieces, learn about them, how we generate them, and actually create an extrinsic. Okay, so of course it starts with metadata, right? One thing our system kind of has to know, like there's no, like right now it's not set up where basically we know exactly how to call balances every time. What we do know is that there's a standard within the Polkadot ecosystem, if you're using Substrate and Frame, that there's a palette called balances, and it has an extrinsic called transfer keep alive, right? There are ways that we could do more standardization in the ecosystem, like we could make more RPCs that are custom or whatever. But in this case, you know, kind of as a developer, you're kind of assuming, okay, I know balances palette exists, I know transfer keep alive exists, so I'm gonna look them up, right? So let's go ahead and do that. So here I have, again, the metadata in JSON format. I'm going to open until I find the balances palette. So I'm gonna keep closing it. Okay, and here, index number 6 is palette balances, right? I don't want storage, I want the calls. And calls are all under type 126. Okay, so that's another place. I'm gonna have to go look type 126. So I'll go to the lookup 126. And look, now I see here the type which has all of the different call variants, right? So here I see a transfer keep alive. It has 2 parameters, a destination, who am I transferring to, and the value, how much am I transferring? And destination is a multi-address. Multi-address, let's look what it does. It has 5 different possible formats, one of which is ID, account ID 32. This is what we want. So what does the multi-address type do? Multi-address in general allows us to use different kinds of address formats in these palettes. So one of the things you'll learn when you do to runtime development is that these palettes are built to be generic. So one of the teams in the Polkadot ecosystem is called Moonbeam. Moonbeam is an EVM-based chain. They do not use 32-byte addresses. They use 20-byte addresses, like Ethereum. They have EVM, but they still use things like palette balances, right? Or the palette balances. So, for example, if I wanted to submit to this call a 20-byte address, it's possible. You see here, there's an option, address 20, and it's a variant under multi-address. So this palette, it supports multiple kinds of address formats, right? And you can even extend it if you wanted to, whatever you want, right? So this is the kind of idea. So, but anyway, the thing that we care about is something simple. It's an ID. It's account ID 32. That's the basic format. So that's who we'll send it to. And then the value, how much are we going to send? That's just the UN28. Basic, right? So I know now that there exists a function that has 2 parameters, and I know what the types are, right? So we can do that. You can see here. Oh, actually, one thing I skipped over. This is not just simple U128. It is compact U128. You can see the metadata shows us that too, right? So we're not passing in a full 128 bits every time, right? Most balance transfers don't use all those bits. So we can use a compact number to save us some extra bytes in the transfer that we wouldn't need to use. So this is, again, where we have a little bit of efficiency in our call. Does that make sense? Yeah? And again, this is where scale is very helpful. So we can see here that we have this balance type, which is a UN28, which is compact. Okay, so let's construct the transfer call. So the transfer call is going to be the palette index, the call index, and the parameters. So we can see here the palette index is 5, but you might ask me, hey, Shawn, don't you remember the palette index was actually 6, right? Let's actually look again. Let's go to the JSON. Let's go to the palettes. 0, 1, 2, 3, 4, 5, 6. It's 6 here, but there's actually, look, there should be a type called the index. Where's the index? Index 5. So even though this is item number 6, this is actually index 5. Let's see if I can find, let's see what number 5 is. So you might ask, what is number 5 then? And I'll show you where that's coming from. But again, this is index 4. Okay, so why? So let's figure out which one of these is the one that caused the difference. So timestamp is index 3. So that's 1 minus 1. Maybe it's system. Is system? System is index 0, so that matches. 1 scheduler is index 1, that matches. So then pre-image was the person at fault. They made everything bad. Index 10. So where is this coming from? So this is coming from the code base. So actually, I need to open up a different repo. If we go to runtime, so one of the things is that the Polkadot SDK is where you'll find all of the libraries for building out runtimes. But part of Polkadot itself being decentralized, the actual runtime itself, the actual code that makes Polkadot run is in a separate repo. And this repo is not owned by Peritech. It's owned by the Polkadot Fellowship, which is an on-chain entity. We'll talk about that later, not a big deal. But if I go into here, let's make this a little bigger so everyone can see. I go into the relay, I go into Polkadot, I go into source, lib, rs, that's what this is. And then I go to decal palettes or decal runtime macro. Construct runtime, here we go. You can see here, look at these indexes. This is where that number is coming from. So here you see, palette pre-image is a 10 here. It's number 2 or number 3 on this list, right? 0, 1, 2. But it's number 10 in the index, right? So you can see here kind of already some of the metadata stuff. Metadata is parsing this code line by line. So it ran over pre-image as the third element. But then it saw actually using the Rust syntax of how we, index enums, we actually gave it index number 10, right? So it's important. If you're going to plan to write your own metadata parser, you can't just do the trivial thing. We have in there which index it is. So you can see that the actual palette index for palette balances is 5, right? And again, there might be some reasons why we did this. For example, I don't want to get too much into the runtime development stuff, but the order of this list affects how code is run. So like, we go through, like if there is some uninitialized function that every palette is going to do something at the very beginning of a block, the order of these palettes is how we will actually trigger the execution. So if I wanted to add in here a new palette, which will execute right after pre-image, my new palette, I could give it index 4, and then I'll have to change this to index, whatever. But then this would be a breaking change, right? All of the transactions which were targeting this index will have changed, right? It will be targeting the wrong palette. So usually we keep these indexes fixed, and we just add, a new number like 40, whatever. And this ensures that we can add a new palette. We can put it wherever we want in this list, but it has a unique index, right? The index doesn't matter. Index is not the ordering. The ordering is happening here, but index is how we uniquely identify which palette we're talking to. Am I losing anyone here? I think this is, I'm just trying to show like, you can't take everything for granted. This is like everything is structured well. You have to handle things well. So going back to this, what we actually saw was even though the balances was item number 6 in this list, because it was item number 6 in the list of the palettes that we included, it's actually index number 5. And we need to use this index to actually reference which palette we want to call, okay? You can see here, the palette index is number 5. The transfer function, its call index is number 3. We can, of course, look that in the metadata. That's no problem. Okay, so now the first parameter, we saw it was a multi-address. Multi-address was an enum, which can then have an address. So the first thing about the enum is that we're using an account ID, right? So if we go back to here, we go to the extrinsic or the lookup. It was 126, right? Transfer keep alive. It's a multi-address. The first part of the multi-address, the enum encoding, is which variant are we using, right? So we're using variant 0, which is the account ID, which is then 32 bytes. So again, we have the first bytes that we're going to include is 00, which is telling us variant number 0, and then of course the address we want to send to. This is why we went over scale, and now you can see how exactly scale is being used, right? There's a type, and we have to exactly encode it in the way we expect. If we didn't include this 00, then it would interpret this first byte as the variant, right? And that would mess up everything, right? So here we have 00 and then the account address. And then the second parameter is a compact number for how much we want to send. So for the balance of 12,345, we have the compact number E5C0. And you can see that this is not 128 bits, right? This is smaller because compact numbers allow us to make it smaller, right? And if you go back to the util, I have this utils, which we linked in the useful tools. You can actually type in a number here, 1, 2, 3, 4, 5. You can make it compact, and you can see the compact representation in scale, right? Okay, So now we have all the parameters we want. The final call will just be putting these all together, right? We have the 05 palette, 03 call. Here is the 00 is account ID, 8EA is the balance, and then at the very end we have the amount we're going to transfer. And I think we can actually test this. We can go really quickly into extrinsics. We can do balances. We can do transfer, keep alive. We can do destination is a account ID 32 of, I guess I want to do Bob, right? But we can do Alice, it's the same shit. And then we do 1, 2, 3, 4, 5, right? And if we look at this. This is what I love about Pappy. Pappy really breaks it down super simple. Look, you can see here that it has this 0503, what we said, the 00, which is the account ID 32. Then, oh, here we go. See, can I see this? Balances is the 05. You see that? Let me make it bigger. This is so pretty. Balance is 05. Transfer keep alive is 03. The ID starts with 00. Alice is that pink stuff, that account, and then the value is that E5C0. It's exactly what we went through by hand, right? And we were able to do this again with the metadata. Just the user types in some numbers, we have the metadata, we convert the types, we use scale, we get the final result. Okay, that was just one piece of the extrinsic, right? So that's just this function call. Now let's talk about this preamble stuff, right? So address and signature, pretty self-explanatory. We don't need to go to that. Signed extensions. This is something that's pretty interesting. Okay. So what are signed extensions? So signed extensions, or we call transaction extensions, is the more broad term, are additional function and information needed to validate an extrinsic. And it's also, this information is found in the metadata, right? And it's called signed extensions. So let's go into the metadata real quick. Let's go to the metadata. We go to the JSON. And if I close up enough of these, signed extensions. And you see here, there's all these different signed extensions with their own types and stuff like that. So let's maybe pull one of them. Let's do check nonce, which is 880. So we go to lookup. Let's go 880. And this expects a compact primitive of U32, a compact U32. So some compact nonce, right? Let's go over all of them. So I kind of have here a breakdown of the signed extensions. Again, it's not important that you know this in detail, but it's good that we just go over it. There's kind of three types of signed extensions. There's one which is functional. So this basically introduces just functional logic that we will check on the extrinsic before the extrinsic is validated. So this doesn't require any data. It's just functional logic. The next one is what we call hidden, and I'll explain that a little bit more in the next slide. Hidden is something where we include some data in the signature, but we don't actually include it in the payload. And finally, we have this I, which is direct. And this is some information which is directly included into the functional logic. By the way, I made up all these names. This is not like official in any way, but these are kind of like how I think about it. So this first one, check non-zero sender. This ensures that we don't accept any calls from the all zero address. Something that's funny, the reason we have to do this is the cryptography that we use, which is SR25519, the all zero address private key is known. That's kind of funny, right? So I know in Ethereum, we use the zero address as the burn address. No one knows the private key. In SR25519, we do know the private key. So we ensure that no one plays with the zero address just to avoid any problems, right? Okay, next, check spec version. We want to make sure when you submit a transaction that it's submitting it to a blockchain with the correct spec version that we expect. If you're submitting it with like an old transaction or something, was delayed and it comes to us and the spec version is different, we'll just reject it because this transaction is no longer valid for our runtime. Same with transaction version. We want to make sure that you're saying it's a transaction, it's the payload versioning that we expect, right? Same with Genesis. So in the Polkadot ecosystem, there's a lot of different blockchains building with Polkadot SDK, right? The only way we can identify two different blockchains are different is with their Genesis, right? So in the payload of the transaction, we include the Genesis to ensure if Polkadot receives this transaction, is this actually for Polkadot, right? By the way, you can notice that these three are all hidden. So I'll show you that trick about how we can do that. But you don't actually have to include the Genesis in the payload. Well, you can sign with it and then check later. So keep that in mind. So mortality, this is ensuring that when you submit a transaction, that it's not valid forever. It's valid within a window. So when you submit a transaction, you don't want the node to hold it for, imagine you made a transaction, transfer all my tokens. But right now you only have $10. What I can do as a node, I can hold that transaction, not submit it to the blockchain, wait till you get more tokens and then submit it after the fact, right? And I can take all your tokens. The mortality ensures that there's a limit window in where the transaction I signed will no longer be valid, right? It prevents, like delayed attacks. Nonce, you should all be familiar with nonce. Nonce is a way that you can avoid replay. So if I have a transaction and it's been included in the blockchain, I can't submit the same transaction again because the nonce would be the same. The nonce should always increment, right? And it also encourages ordering. So if I submit 2 transactions, one after the other, using the nonce, I can know the ordering of those transactions versus the transaction pool, which is kind of crazy, right? Check weight ensures that we have enough gas and fees to pay for the transaction. Charging the payment, you can see this is just a function. This is how much fees and tips we want to include. This is something that's not really important. And then the metadata hash. We also ensure when the user constructed the transaction, they did so with the correct metadata. So this is so important when we're talking about with the ledger. So ledger if you don't know, is a hardware wallet, right? This hardware wallet is very small. It's like a microprocessor. It's really meant to be a low-weight device. One of the things that we struggled in the Polkadot ecosystem is to avoid blind signing. By the way, many other ecosystems still have a ton of blind signing. Actually, as recently as a few months ago, like $3 billion was hacked, something like that, by a blind signing attack. You can look that up. But blind signing is a really big problem, where basically you have this little ledger. It says, hey, you want to sign this message? And all it shows you is a bunch of zeros and ones, right? Like, that's not helpful. You don't know anything about it. But of course, as we told you, the metadata in Polkadot is quite big, right? So all the information needed to actually parse what those zeros and ones mean is it's too heavy for the ledger. So what we can actually do is, just like the storage, we can create a Merkle proof of the metadata inside of the full metadata, right? So if you only want to know this function is 0503 is transfer keep alive with these parameters, instead of giving you the whole metadata, we can Merkleize the metadata and give you just a proof that this transfer function is correct for this encoding, and it matches this this metadata hash, right? So we can basically do exactly the same thing we do with the storage verification. And then when I sign a message with my ledger, I'm including the hash I used for the metadata, so that when the blockchain receives it, if it doesn't match, it'll be like, nope, I'm going to ignore this. Because it could be that I can make a ledger app, which is malicious, which would show you, oh, this is just a basic transfer, and it actually is taking all your funds, right? But then that Genesis, that metadata hash would have not matched. So then even though you signed that message, and even though that message has a valid signature, the blockchain wouldn't accept it. This is yet another way that we really, really look to support trustless, verifiable systems. And again, this is like pretty much you can think of the ledger as like a light client in some ways of all this signing stuff. So we built this in. It's super cool. Other ecosystems don't have this. I mean, really, you're mostly doing blind signing, or you're doing like fixed signing. Okay, so let's talk about this hidden data. So I mentioned a few things in this sign extension can be hidden rather than be explicitly included, right? So for example, nonce has to be included. When I submit a transaction, I'm going to tell you what nonce I'm going to put on this transaction. I'm going to sign that whole message, and then we're going to check, okay, is the nonce exactly one more than their previous nonce, right? This is how we do things. But things like the Genesis hash of the blockchain, that is something that I know and something that the client knows. If we both know it, we don't both need to include it. It's just redundant information, right? So what I can do is I can take that Genesis hash, I can sign a message with it, and then I can just not include that part of the message when I submit the signature, right? Whenever you do a signature, you have to include the message and the signature. You can verify that it was signed correctly. So I will sign the message with the Genesis hash, but I'll send the message without the Genesis hash. And then you, as the blockchain, knowing that this will not be included, you will add back the Genesis hash and then verify the signature. Imagine how many bytes we can save, like how much data is redundant that the blockchain already knows, right? So basically, we can sign that information, showing the user acknowledges that this is what I want, and the blockchain can inject it. And if the blockchain injects a Genesis hash and it doesn't match, the signature won't validate, right? Does that make sense what I'm saying? Yeah, quite, can we take the mics in question? So what I do here is I do a basic example with a Blake. Like a hash is almost similar to a signature, a little bit less, verifiable. But basically, I can do hello world plus Genesis hash, create some kind of new hash. And then when I send the message, I only put hello world, and the blockchain will include their Genesis hash, and they should get the same final hash at the end. Okay.
So regarding check genesis, if it's a bridge transaction, I want to verify the source and the destination blockchain both,
Yeah.
the genesis of both. So in that case, how do we specify both the genesis blocks?
So what we're talking about is extrinsics. When you're doing chain-to-chain communication over a bridge, you'll use different channels, which by the way that the XCMP system works, you know where the transactions are coming from. Like again, this is a breakdown of an extrinsic, which is not the same message format for bridge-to-bridge communication. So I would have to explain that. But I'm sure that in the bridge-to-bridge communication, they have all the proper data points for who should be getting it, who's sending it, etc. Right? Again, you're right though. Like for example, a bridge, a blockchain can't sign a message. They don't have a key, right? So what actually is happening is that the way the XCMP messages work and the way that networking works, I as the relay chain, I'm accepting messages from a parachain, and I'm basically saying this message is coming from this parachain. Anyway, we'll get into that later. There's a whole section on XCM at the end of the academy. Another question?
Yeah, like one question in the previous slide.
Previous
all
slide.
yeah, all these like function is imported by default, or like the developer, like
This is the developer chooses. So again, let's go back to here. If I go to the Polkadot repo, the runtime, where's that? So the green is runtime. If I go to signed extension, wait, extension. Here, look at this here. So there's this transaction extension block, and you see all of those checks. So you as a developer can actually write your own extensions. You can write your own
I
extra
can
validation
override
and
as
add
well.
it.
I can override, like change the functionality, how it works.
Yeah, you can change it, you can write it, you can do whatever you want, right? Yeah, exactly. And you can even remove some that you don't want, you know. If you want the 0 address to send messages, you can just comment this out and it will all work. And again, the metadata is what's propagating to you which ones do I need, right? Yeah. Okay.
Yeah, one last question.
One more?
Here, yeah.
I guess two questions if I can. For when you were talking about constructing the transfer call, what
Yep.
exactly did you do to Bob's address?
Sorry, say one time. What is Bob's address, what you asked?
No. What did you do to Bob's address?
Okay, what I did to Bob's address. I just encoded it into its bytes. So this is a string. Okay, this is a very good question. A address is just U832, right? It's just 32 bytes. So the address is always just 32 bytes, which is exactly what this is. What this string is what we call an SS58 representation. So SS58, I think is a Bitcoin thing. And it's an address format. Okay, well, that's not what I wanted. Well, maybe but it's not a substrate thing. I think it's bigger than Polkadot. But basically, it's a special address format which allows you to have certain guarantees around. Let's see, convert. Certain guarantees around what you see. So, for example, in Polkadot, all of these bytes don't mean anything. But when you convert it to SS58 format, it allows a certain chain to have a certain representation of the address. So all the addresses in here start with like a 5 or whatever. And then all the ones in Polkadot will start with a different one. That's here, Polkadot is all start with like 14 or something, or Kusama's F and etc. So you can see here the same exact public key on different networks has actually a different address look. You see what I'm saying here? This exact thing. And so what this ensures is that if I'm using some kind of UI, let's say I intend to do a transfer on Polkadot, but somehow I copied the Kusama address. That's something that the wallet could be like, hey, I think something went wrong here. Even though the bytes on Polkadot and Kusama are exactly the same, the address format can look a little bit different and it can warn the user, hey, maybe you're doing something wrong, right? But this is basically the SS58 representation. This is the address that you'll see on block explorers. But we know that the real address is only 32 bytes. It's always actually just this hex. So all I do is convert to the 32 bytes.
Got it. And I guess the one other thing I had a question about. So I guess we're like salting basically the transaction details with the common data between the two nodes.
One more time. Sorry.
So I guess when we add the Genesis block data to the I guess the message, is it basically like we're just salting it?
What's the word you said? Assaulting?
Salting?
Assaulting. I don't think it's assault. I mean, it's literally. I mean, assault. So assaulting is what I do with passwords. And when you add assault to a password, it's like obfuscating the hash of the password so that you don't have like two people with the same password that they match, right? It's not quite doing that. When you add the Genesis hash, it's basically saying, I made this transaction for this blockchain. That I'm not like, because again, Kusama and Polkadot, or your parachain, they all use the same libraries. They all use Polkadot SDK. So if I construct a transaction without the Genesis hash, it could be that I could send the transaction to multiple blockchains, right? But with the Genesis hash, I ensure that that transaction is only valid for one blockchain.
Okay, so the Genesis block is like required.
It is. It's something that without it, your chain won't be safe.
Okay.
Yeah. Okay. Yeah. I mean, the idea here is replay attacks, like nonce, era, Genesis hash is all about replay attacks, where basically you have some signed message with a private key, and I'm replaying that on multiple different blockchains, and you want to avoid that, and that's what these checks do. Right, we can do one more, and then let's keep going, and then we can answer more.
Related to this part, because like it's a follow-up question related to this part, because is it enforced for like the DAB developer who enforce adding this hidden information for the Genesis block, or
so the runtime developer is the one who is actually holding the burden of I have to do all these checks, and as a DApp developer, you have to follow all the checks they require, otherwise your transaction is not valid.
So like in the blockchain itself, we are protecting, like in Polkadot and Kusama and stuff like this, we are preventing the replay attack from a chain, like in different chains, by like enforcing this. Is that correct?
Yeah. So like as a blockchain developer, I put these checks here. You as a DApp developer, you have to follow these rules, otherwise it's not valid. But like we are imposing onto you that these are the checks I need to keep my blockchain safe, right? And you as a DApp developer, you can't bypass these checks. Like you can't do things in shady ways because we've enforced it at the blockchain. Okay, let's keep going. We have time for questions at the end. Okay, it's only halfway through this thing. Okay. Okay, so we went through that. So there's a bunch of different types, right? And they all have different things. We showed you how to do the hidden, makes sense. Again, it's just all about saving, like, imagine we're making a blockchain, it's gonna be doing millions of transactions per day, right? Every single byte we can save actually saves a lot. And one of the major limiting factors in blockchains today is networking speeds. Like, again, global decentralized networks, that is where the bottleneck is. Okay. So to create the signature, we will sign the call payload and then all the extension data, right? So we have the call payload, which was that call that we created. We have all the extension data, which is including the hidden data, right? And we put that all together into one blob. We sign that, right? Now, if that payload is bigger than 256, we hash it first, and then we sign that, right? Because the hash is already a distinct representation of all the data inside of it, right? And it saves basically compute time from the signature. Because when you do signatures, obviously it gets more complex the longer the payload is, right? So we just hash it and sign it, and then of course we send at the very end. So we can see here the signed payload. So if we go to the Polkadot, we can do struct signed payload. And you can see here the call, the extensions, and any implicit. This is like the hidden stuff, right? And then, I guess I didn't say this. The last part is that we, of course, send the payload as we had originally, all the way back here, but of course, without the implicit information, right? So the real payload will look like this. With the extrinsic version, all this preamble stuff, the function call, and then process it. Okay, any questions about making a transaction? Yeah, we have one more in the front. Can we get that to the front? Yeah, definitely look. I would encourage you to all look at the code. You can see a lot of code comments. The payload's been signed. You can see the functions that we imply onto it. You can even see here, this is that code which does the, if it's bigger than 256, like read this code right here. If the payload for the signed call is greater than 256, we hash it. Otherwise, we sign it. That's exactly like what I just said is exactly here in the code, right? Okay.
Yeah, you've answered the question.
Oh, great.
I was just interested in the converse. What happened if it's less than 256?
Yeah, no, it just you sign it directly. Yeah. Okay. Any more questions? If not, we'll go to part 4. Okay, we're following. Okay, good. Part 4, submit and track a transaction. Okay. So we're talking about the transaction pool. So what have we done so far? So we have done all the backing for storage. We were able to read storage. We were able to create a transaction. We actually have now, we can submit the transaction. Alice sends Bob some money, right? What happens after that? What happens to the transaction in this scary, decentralized peer-to-peer network, right? Let's follow it. So The light client can submit via RPC to the full node, author, submit, and watch extrinsic. This is over WebSocket connection, right? It will accept the extrinsic payload, and it will return a subscription ID. And then basically from that point forward, the node's responsibility is to push updates to the client with any kind of updates about the transactions through the subscription, right? This is a normal WebSocket subscription, okay? And the WebSocket or the JSON RPC that we use is JSON RPC. I think we'll have a presentation on this afterwards. Okay. So there are different stages of the subscription. So when you submit a transaction, it'll be into one, you'll get updates in one of these states. Future, which means that the transaction is valid, but maybe is not ready to be executed right now. For example, the nonce is higher than the last nonce that we know, right? Ready, that means it's ready to go. Broadcast, this is telling you that the transaction is valid. It's maybe not future already, but it's being propagated to other nodes on the network, right? It's being broadcasted, and this vector is a list of other nodes on the network that's getting your transaction, right? In block, this means that it has been included in a block, but that block hasn't been finalized yet, and it tells you which block hash and what transaction index it is. And then, of course, finalized, when that transaction is not only in the block, but is actually part of a finalized canonical chain, it tells you, hey, it's finalized. Here's the block hash again. Here's the transaction index. You can really know that your transaction happened, right? And then, of course, there's the invalid. If the transaction is itself not actually valid, it will be invalid and dropped from the pool, right? So in this whole thing, there's this thing called a transaction pool. And the purpose of the transaction pool is basically to move the transaction between the different stages of the transaction lifecycle, right? So whether it be future to ready to invalid, transaction pool handles all of that. Now, one thing important to note is that all of the transaction validity logic is exclusively determined by the runtime, right? The client, it is the one that has the transaction pool. But it has a set of calls that it makes to the runtime to actually understand the logic. The logic of what is a valid or invalid transaction, that's all determined by the runtime, right? The runtime is where the real logic lives, right? So all of that check genesis, check whatever, as I showed you in here, that information, the signed extension, all that stuff that we're doing to check that the transaction is valid is part of the runtime of the blockchain, not the client. But the transaction pool is part of the client. Does that make sense? Transaction pool is part of the client, but it calls into the runtime. It asks, hey, is this valid or not, right? Cool. Transaction validation should be cheap, right? So when we're validating a transaction, we're not expecting the user to pay fees. For example, it could be as simple as the signature is wrong, right? If the signature is wrong, we don't even know who to charge a fee to, right? So we cannot do things like read storage or do any kind of heavy operation in transaction validation. It should be very cheap stuff. Signature verification, basic number verification, all that kind of stuff, right? We can't do any kind of heavy operation. Otherwise, there's opportunity for us to get DOSed, right? They basically someone to submit a lot of bad transactions, we're doing a bunch of heavy work, and no one's paying any fees. Our network will suffer as a result, right? And transaction pool is an entirely off-chain operation. So the transaction pool itself cannot lead to any state changes. You cannot, when you actually process the transaction, change the state. But it shouldn't be that the transaction being in the pool will change state, right? All right, cool. So what is the basic transaction pool validation? So we do all the basic checks. And this all comes from a lot from the transaction extensions, which is why we talked about it, right? So is the signature valid? Is the nonce valid? Is the error ongoing? Do we have enough balance to pay the fee? Is the transaction targeting the right chain? All the basic checks is what we're doing in the transaction pool. Is this even a valid transaction? We're not guaranteeing that the transaction will complete successfully. We're not guaranteeing that. All we're guaranteeing is that the transaction itself has all the right pieces to be past the basic validation check, right? We don't know until we actually execute the transaction what the result will be, right? And you can find here in the code the validate transaction function. And you can see that the result of processing and validating transaction, we return this struct called the transaction validity, right? So let's look at that. So transaction validity is a result with either a valid transaction or transaction validity error. And you can see here, if the transaction is valid, we get this back with this struct. So it will tell us the priority of the transaction, how long it's valid for, and if we should be propagating it, if we should be broadcasting it to other nodes, right? Additionally, it has this really important stuff we'll go into. It has requires and provides tags. This is what allows us to order the transactions and ensure that all the transactions are being ordered correctly, right? Okay, that's everything. So Of course, if a transaction is invalid, we saw here like the transaction validity error or something like that, we can generally ban the transaction. So we can basically take the hash of the transaction, put it into some queue, and say this transaction is banned for a while. And usually the duration by default is, I guess, 30 minutes, right? But yeah, I mean, basically it ensures that someone's not spamming the same transaction over and over. We're not getting it, gossiped to us a bunch of times. We just, ban it from the pool. But it could be vanilla. You don't want to ban it forever. Why don't you want to ban it forever? Someone knows. Why don't you want to ban it forever? You can just scream. I'll just repeat. Yeah, it could be valid later, right? Exactly. So exactly. So a transaction could be invalid because the nonce is not correct or whatever, but at some point in the future it could be valid, right? So it doesn't make sense to ban it forever. We just ban it right now so we don't get spammed it, right? Cool. Okay. Transaction gossiping. By the way, I do talk about the ordering. Okay, cool. Transaction gossiping. So yeah, so once it's determined to be valid, the node starts gossiping the transaction to its peers, right? Immediately. It just starts gossiping it. And then, of course, the subscription is updated to broadcast with all the vector of people that have been getting your transaction, right? And gossiping will repeat, on and on. So you get gossiped it, they gossip it, it goes all across the network. That's peer-to-peer stuff, right? Normal. Okay, now let's go about ordering. So you saw in the valid transaction struct, there are two parameters, provides and requires. And I told you that this is what helps order the transaction in the transaction pool, right? So a transaction will not be ready until some transaction provides what it requires. So let's look at that in detail, okay? So the most basic example is nonce, right? So imagine that I have a nonce, and I submit transaction with nonce 5. And I have in the blockchain, my nonce is 3. And then later I submit a transaction with nonce 4. Nonce 4 provides nonce 4. Nonce 5 requires nonce 4 to exist, right? So this is basically like some transaction provides the thing that I'm looking for, that I require for me to be active, right? Nonce also does other things. Nonce, of course, does ordering in this simple case. It does replay protection, so you don't do the same thing twice. It also prevents double spend, right? It prevents, that there's only one possible canonical chain where your transaction will be valid on that chain, right? So even though you could have 2 different spends or 2 different whatever on different forks, or you could even sign a message twice with the same nonce, only one of those 2 nonces will be valid, right? You can't actually double spend. Anyway, with provides and requires, again, this nonce idea is the most simple kind of version of how we can expect it. So when we actually look at inside of the transaction pool, the provides will be something like a tuple of the sender and their nonce. And then the require for the transaction will be the sender plus the nonce minus 1. So again, for my transaction to be valid, I'm looking for the last nonce to be there for my sender, and I will provide this new nonce. For things like UTXO, like Bitcoin format, the simple would be that someone provides a UTXO and someone requires that last spend exists, that last unspent transaction exists, right? And one of the things that's interesting, and when we talk about the Polkadot SDK, it is designed to be a very general blockchain framework. So we could have just designed it with nonce, and we could have just made it simple like that. But we actually made transaction pool more abstract with this provides requires thing, so that you could build a Bitcoin-like blockchain which has no accounts on our platform, right? If you assume nonce, you are assuming an account-based model, right? Our transaction pool allows for a more general model, so you can build Bitcoin, you can build whatever kind of system you want, right? Okay, so let's go and look at some examples. So transaction ordering. So here's a transaction. Transaction A, it provides nothing, it requires nothing. Will it go into the ready or future? I think I heard someone say ready, and that's correct. It doesn't require anything, it doesn't provide anything, you can just go. It's good, right? Next one. Now transaction B provides 2, requires 1. It will go in future, obviously, because we don't have anything with 1, right? C provides 3, requires 2. We have 2 there, right? But no, it goes to future because 2 is still in the future, so 3 is in the future, right? Finally, D shows up. It doesn't require anything, but provides 1. Suddenly, all of them are ready, right? And they're all ordered to. They're in the right order where each one that is required happens after the one that provides it. Super simple, right? Makes sense. Okay, cool. Nothing too crazy. And I guess in your mental model, if you actually were to do this, it looks like a graph, right? You're creating a graph of like dependencies, and then basically you want to linearize that graph at some point, right? You want to just make it a straight line from all the data points. Cool. Okay, so that's the most basic transaction ordering. There's even more. So now imagine that you have some ordering. There's a race condition. Which of these two will we do first? So the first thing we do is we look at which one was there the longest. So from the viewpoint of the block author, which transaction have I known about the longest? We'll put that one first, generally speaking, right? The other one is which one. Yeah, wait. The shortest longevity goes first. Yeah, time to live. So whichever one. Well, sorry. I can read my slides, not just talk. The first one is whichever one will end first. So if I have in here the transaction is only valid for a certain amount of time, obviously I want to get the one that's going to be dying sooner into the transaction pool. Then of course the one which I see first will happen after. There's also again this priority. We saw that there's this priority function. This is actually controllable by you, the runtime developer. So you can determine the priority of any transaction. So you'll even have a jumpstart. So beyond the nonce checks, you can determine the priority of a transaction. For example, I want to make a blockchain where runtime upgrade is high priority. So even if you submit a transaction, that's like a basic transfer. If I see a runtime upgrade, it goes front of the line, right? You can control that. Let's say that you want a blockchain where you're the CEO and you want all of your transactions to go first. You want to MEV everyone, right? You can do that. You can make some kind of signed extension which checks, is this address Sean's address? Put them in front of the line, right? Above everyone else. So you control the priority and you can do whatever you want in that code. For us, in Polkadot and all substrate chains, the default priority control we give you is this thing called tips. So what you can do is basically you can bribe the block producer. This is true for any chain. Basically, the transaction costs a base fee, but I can add extra money called a tip, which encourages the block producer to add my transaction. And so basically, the more tip you give, the higher your priority, and we'll make sure to include you. So if there's a blockchain with a lot of congestion, right, a lot of trading, not all the transactions will make it into the block. The more you bribe the block producer with a tip, the higher chance you have to be included in the block. Your priority will go up. Make sense? Okay. And then, of course, eventually, your transaction's in the pool, it gets verified, it gets ordered, and finally it gets included into the block. And yeah, then it gets executed. And it gets put into a new block. Okay, any questions on the transaction lifecycle? Yeah, let's bring the microphone around, please.
Microphone's coming. Hello, which one takes more priority, the tip or the shortest longevity?
I think tip is first. So it'll be like the required check, like the non-stuff first, then priority, then TTL, then longevity. And so priority will be the top one. But I think you literally could change that by changing the order of the transaction extensions. Like depending on which order you put them in, is the order which like they will, check first. Yeah.
I have a couple of questions.
Okay, sure.
The first one is related to the future transaction, the status itself. How long it should be there in the mempool with future status, the lifetime of it?
So all of that is controlled by the client. So there's no fixed rules there. When I run a Polkadot node, there's all these flags, and one of the flags controls the pool, like how long you want to have it in the future until you want to drop it, how many you want to keep in there. Like even there's limits to how many transactions are in my pool, right? So like, I can control all those details with the client flags.
Okay. The second question is related to the priority flag, if you can call it flag. Is it like in the same account or in general, like in the, it's kind of like transaction with priority, so like it will be included?
So what was the first word you
like
said?
I was confused. I'm not sure I got it correctly or not. Like when we have a priority, it is the same account. So let's assume I send 2 transactions or 3 transactions, one with nonce 1, second with nonce 2, and the third with nonce 3. And the third one has a priority. In this case, will be included first?
No, it can't, because obviously it requires the other ones.
Yeah, because I was confused.
Yeah, so the provides requires is the first thing. Like you cannot break that rule. Okay. But within transactions where they are equal in terms of the provides requires, then priority, then longevity, then TTL, whatever. Okay, that will be what happens.
Got it.
Is there any situation or incentive for an attacker to put futures in the transaction pool that have no intention of ever becoming ready?
I mean, you could
timeout?
definitely spam a node. So one of the things I'll mention here is that running a node is its own set of like OPSEC practices, or like I don't know, like it's its own field. Generally speaking, running a public RPC node is not, it's not that it's not safe. You have to put like a firewall, you put like a Cloudflare or whatever to prevent spam. And you should be prepared that people can spam a bunch of transactions that are going to be useless and whatever. But I think that the client flags have basic rules for how you drop transactions, ensure the pool is filled up, all kind of stuff, right? But I mean, if you are a public RPC node for a blockchain, you should expect to be attacked.
Cool.
Yeah.
Hi. So before we validate any transaction, right? We are only doing read operations on chain.
Even read operations, very minimal. We should not do a lot of read operations. Very, very minimal read operations. But yes.
Okay, so there's no write operation. And I have opened a subscription ID. I'm sending the validation information to the Light client. How would I know that the block author is not charging me a lot of amount for a transaction? How do I verify that this charge for this transaction is actually
the right amount? You're asking basically when I submit a transaction that I'm not getting overcharged.
Yeah.
So that's the answer is that the state transition function is part of the state. It's deterministic, right? Like the state transition function is deterministic. I could, for example, do like a pre-run or dry run and see all the fees, and when I run it, it'll also be the same, right? Now it doesn't stop, for example, someone to change the runtime, and then the fees change, whatever. But practically speaking, it's like the fee charging is itself a deterministic mathematical thing. So you should know how much you're going to get charged before you make a transaction.
So the block author has no say in what it is going to be because the state transition function already decides and the.
But okay, I think though there's also like a wait, that's a good question. Give me 1 second. Is one of the side extensions how much fee you're willing to pay? Someone know? Because I think you're making a good point. Basically,
no, the fee is deterministic in.
No, but remember the weight to fee ratio could change depending on the traffic of the network.
Because when you dry run it, not dry run, but calculate the fee, it gives you the maximum fee that you will pay depending on the storage.
There is, right?
But the only thing that can be is lower than the maximum that it gives.
Yeah. So I think as part of the transaction, you put the maximum fee you're willing to pay.
Yeah,
right?
More or less, yes.
And it can only go less. So that at least determines that you won't get overcharged, right? Yeah. Yeah, good point. Anything else?
I think I was looking at that slide that said the transaction pool first is low cost, fast to validate operations.
Yes.
So I guess that's like different, or maybe I don't know if it's different because I guess low cost doesn't necessarily specify if it's like necessarily like a higher fee or like a lower fee.
No,
per
low
guest.
cost. I'm talking about computational cost.
Oh, okay.
Yes, I'm not talking about computational cost. I'm talking like doing a signature verification is low cost. Doing a storage read is a high cost.
Okay, so that takes priority over like the actual fees that are being paid.
So, sorry, when I say low cost, again, it's not about fees at all. It's about when I do transaction verification in the transaction pool, I'm trying to ensure the transaction is valid without my computer having to do a lot of work. Like if I had to calculate all the prime numbers in order to get your transaction to be valid, that would be like, I would spend the whole time for years, just doing your transaction. I want to make sure that I spend as little time as possible to ensure the minimum validity of your transaction before I go and execute it.
Okay, I guess I was just thinking about it. I don't know if Polkadot. I guess I thought that Polkadot also had like this kind of like ordering by, at least like by gas price, like Ethereum does.
No, so Ethereum does not have ordering by.
At least not anymore. Yeah.
Yeah, I mean it has a tip, so that you can pay more money, and then that tip will with the priority. Yeah, but the exact way that we do the fee calculation is not the same as Ethereum. We don't have like I know when you do an Ethereum thing, you do like a gas to ETH number. I don't think we have that.
Okay.
Yeah, but you could. I mean, as a developer using Polkadot SDK, you could build that. And again, Moonbeam has built that into their blockchain. So however, like I'm showing you some of the basic stuff. You can design whatever things you want. So actually, let's go back to the code base real quick. And here, this pallet transaction payment, charge transaction payment, you could literally just in your code comment this out. Shawn's pallet, charge transaction with gas to dot, right? Like you can design your own and you can do whatever math you want in there, right? And then the whole thing is that the point I'm trying to say here is that at some point your logic will execute, and you have the only ability you have to influence is by updating this. So the whatever logic you do needs to turn back into one number, which is priority, right? And so at that point, it's up to you and your runtime to determine how do I determine priority based off of whatever inputs they give me, and then you do it, right?
Thanks.
We take two more if that's fine, Shawn. Yeah.
What's one more question?
Two more questions. Is that
yeah?
fine?
I mean, if there's two more, then we have one last presentation.
Okay. Yeah. Let's go for
Okay,
it.
two more.
Hello. In which case we shouldn't propagate a valid transaction?
Which we should provide what?
In which case we shouldn't propagate a valid transaction? I see the propagate flag here.
So the valid transaction is, okay, that's great. Let's look at one of these things, right? Let's look at this, let's look at the check weight. So somewhere I should find struct check weight. No, sorry, it's gonna be in the Polkadot SDK. Struct check weight. So this is a signed extension. And this is a struct which has a function which can return either a result 0 or transactionability error. And there should be somewhere here that returns a valid transaction. Here, like do validate, right? This function. So imagine that the API we're exposing to you is, you can write as many pieces of logic as you want. At any point, you can return either it's valid or it's invalid. Imagine I have 10 checks. Checks 1 through 9 can all be valid. If check 10 is invalid, the whole thing is invalid, right? At any point, if any of the checks are invalid, the transaction is invalid. But if it passes through all of them and it remains valid, it stays valid. So when you're asking when should you mark it valid or invalid, you're the one writing the check. You tell me, what am I checking for, right? And you're choosing, do I want to make it valid or invalid? So I'll give you an example. I can make a signed extension that says, Shawn is not allowed to use my blockchain. So Shawn has his private key. I'll make a check, which if this private key is calling me, invalid, right? Immediately. Otherwise, it's valid. So you're the one who decides what's valid and invalid. We're giving you an API that you can submit this information, and the transaction pool processes it and understands, oh, it's invalid. I don't care why. I don't even know why. I just throw it away. Make sense?
Yep.
So I think the thing I would want to get from you here is that I'm kind of showing you. Let me see. There's a piece. Let me repeat this because I think this is my first time doing this kind of presentation here. Here, piece 1. Transaction validation logic doesn't happen in the pool. It happens in the runtime. So the pool is the one organizing all the transactions, but it's not the one who actually knows how to organize them, if that makes sense. It can only, with the priority and stuff like that, and transaction validity, it can keep them in there and do basic, but it doesn't actually know how to give it priority. It defers that to the runtime. You as a runtime developer, you can do whatever logic you want on this thing, as long as it's cheap. I mean, you could actually do not cheap stuff, but your blockchain would be attacked. But you can do whatever you want, keep it cheap, and then you can send information back to transaction pool. This is how you should behave. And the interface for sending things back to transaction pool is this. The transaction validity, my runtime can either give back to transaction pool, valid or invalid. And if it's valid, it can give back information. What's my priority? What's my longevity? Should I propagate? What's it require to provide, right? And so then the transaction pool with this information acts on whatever it can act on, but it doesn't know how it got there. All of your logic in the runtime kind of hidden is what determines this, right? Okay.
My question is, so once you have the priority and the tip, right?
Mhm.
And then you know how to order it based on the DAG. It's some sort of topological sort, right? But then you get, like, is it completely linear? Like that will be the canonical ordering in the block, like from the block producer. Everyone has to follow that ordering, like, because obviously it's a topological sort.
Yeah.
Yeah.
So I think you're making a good point here. So if I made my own client, I do not have to follow those rules. Like if you make a custom client, you can follow pretty much any rules you want as long as the runtime allows those rules to happen, right? So you do not have to follow the priority that it gives back to you. Yeah. Did that answer your question?
No, I'm also curious about, like, let's say,
so this provides and requires that you have. Let's say there are transactions that can have the same sort of ranking in that order.
Okay.
Right? Then you can put them in any order. Like it doesn't.
Yeah, but then so this is the tiebreaker. So if you have two transactions that are kind of the same, the tiebreakers for our default chain is the TTL and then the other thing. What is it called? Where's that slide? Anyway, it's like it's the other stuff, right? It's the TTL, etc. Anything that's they're the same, we look at other stuff. And then whenever even all those are exactly the same, then you just put it in any order. It doesn't matter, right?
Right.
Yeah. Again, one thing that's important though is that the transaction pool is part of the client. It's not deterministic. It doesn't have to be. It just has to be, the runtime just has to make sure that these transactions are actually valid, right? Okay. All right, let's keep going forward, huh? Last slides. Okay, let's finish the whole picture. Okay, so what do? We read storage, we checked by balance. We constructed a transaction, we submitted the transaction, then we watched the transaction go into the network, across the transaction pools, gossiped around, validated, prioritized, ordered, and included in a block. Finally, what is happening when we say it's included in the block? How are we actually updating the state? That is the state transition function, right? That's the last piece. Okay, so we enter the runtime. So once the transaction has been included in the block, we need to execute the state transition function. At this point, all of the execution is happening inside the runtime via runtime APIs. So what's really important and something that you'll be hammered home over and over is the difference between the client and the runtime. Okay? So really, even the way that you see the structure of the Polkadot repo, you will see this client runtime separation, right? And so it's something that we talk about over and over, and it has a lot of important features. So one thing is it's important for forkless upgrades, sure, but it's also important for parachain validation. We actually use the fact that the client and runtime are separate to be able to allow for parachains and rollups to exist. It allows the creation for third-party runtime SDKs. So right now, we are showing you how to build on Frame. Anyone here could build their own runtime SDK, right? And because we don't require, because we separate things out, you can use existing clients and have your runtime work, right? And then, of course, it enables support ultimately for native applications. So at some point, depending on what VM you use within your client, you could run, normal applications. So, like, for example, right now we're using WASM. You might hear that JAM is using RISC-V. Within the separation of the client and the runtime, you could imagine running any kind of RISC-V application within this executor, right? So it allows for a lot of things. Something else is broken. I must have missed a thing. It seems like, so what the last picture that was broken was because I was missing a backslash in an HTML element. So tisk, localhost. Okay, let me just get the picture that I want to show. Blah, 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 blah. Oh, this is the picture, right? Okay, so again, this is kind of the high-level architecture. And if you're part of the protocol track, you will get to this a lot more, right? But basically, the idea is that there's this node and there's the runtime, right? They're separated. The runtime is the application logic. It is the state transition function, right? It's how we execute the block, right? It's stored in the chain as a WASM blob on chain. It's upgradable. You know about that already, right? Then you have the client. This is the node, right? And there's basically a meta protocol. This is a native binary, so something that you actually run on your computer, right? And it has a WASM executor. It is a thing that executes the WASM. It acts as a VM and runs your little WASM blob, right? And it has all of the other things in there, like the database, networking, mempool, consensus. All of those things are included as part of the client, right? And we call it the node, the host, the client, etc. Right? This is all the kind of same term. But it is the actual program running on your computer. Okay, an analogy that we really like to use, I think it really breaks things down, is that it's like a game console. The client is like an Xbox, right? And then the runtime is like the game disk. We know that all these different game publishers, they publish their game in in a special format, which the Xbox understands, and allows you to take your Xbox and turn it into Halo or SSX Tricky or I don't know Street Fighter or whatever you want, right? And it will basically turn your console into that game, right? So really, what we talk about here is that the client in Polkadot world is a WASM executor. It can execute any kind of WASM file that follows our format. And then all of your blockchains that you build are basically custom runtimes, custom WASMs, which are executed in this client. And again, some of you might have seen this OmniNode thing. OmniNode is exactly that. OmniNode is a general game console. You can build a custom runtime, put it into OmniNode, it will run the blockchain. Okay. Now, between the client and the runtime, there are two sets of APIs. The runtime APIs, which are the APIs used when the client calls the runtime. So I, as a client, am talking to the runtime, like, hey, is this transaction valid? That's a runtime API, right? Then you also have the host functions. These are the functions where the runtime calls the client. Runtime might say, hey, is this signature valid? Hey, what is the storage here, right? The runtime doesn't know this. The client knows this, right? The client is where the database is, right? So that is, any kind of host function goes there, right? And so passing data between the runtime and the client, generally speaking, is pretty slow. So you should be pretty explicit about when you want to use this, right? That makes sense. All right. So one thing that you're gonna kind of see, again, especially if you get deeper into the runtime stuff, is this idea of opaque encoding. So the client and runtime interface shouldn't change frequently, even though both the client and runtime themselves change a lot, right? So the runtime can be upgraded all the time. Even the client can be upgraded. You need to do like not a hard fork, but you need to do like a upgrade with your community. But these things can upgrade a lot. But the interface between the client and the runtime should be very stable. Because again, your client not only needs to execute the current runtime code, it needs to be able to run any of the code in the past. If you need to sync a chain, right, you need to run the runtime, the whole history of the blockchain. So one of the ways that we allow us to have a consistent interface between the client and the runtime, even though the runtime changes all the time, is to have this opaque encoding. Opaque encoding basically means we take all of your nice, beautiful structs and we just turn it into a vector of bytes, right? So basically, I have some structs, like an object for a user or some transaction, whatever, and it has some well-known format. It's like, here's the call, here's the palette, here's the thing, and here's the parameters, etc. I take all of that, I encode it one more time into a vector of bytes, and then I pass it over the line. So the client in this case is kind of like blind. It does not know really what it's sending. It's just sending bytes over, and the runtime will go interpret those bytes and turn it back into the known types. But what's nice is that we can keep the interface between the client and the runtime the same because it's always just passing bytes, right? So it doesn't change as the runtime itself evolves, right? Does this make sense? So we call this opaque encoding or double encoding, and you'll see this when you get deeper into building stuff with the runtime. You'll see basically that the client and the runtime, they don't really know what they're doing to each other. There's kind of this kind of like a hiddenness to them, but it all works in the end. You have a question? Yeah.
Yeah, I was just wondering, how does this work with metadata? Like, if I wrap something in an opaque value, is that struct still visible in metadata?
So okay, so this is a great question. So when I'm talking about the opaque value, mostly it's about the specific interface between the client talking to runtime. So I'm talking about the runtime APIs and host functions. Once you're in the runtime, it knows what types to expect. The client, similarly, when it's receiving stuff, it also knows what types to expect. But just between this interface, it's double encoding it.
Okay.
Yeah,
I think I understand.
You should suspect in most places we are still doing type safe stuff. Okay. All right, let's keep going. Okay. So I mentioned here. So one of the reason why I bring this up is because when you submit extrinsics, they're not opaque. You're submitting extrinsics in the format we described. They're kind of well understood. But when you include the extrinsic into a block, they become double encoded. Because again, the extrinsic was valid for a runtime at that point in time. But the block lives forever, right? The runtime can be totally different over here. The client can be totally different over here, right? So when we actually store the extrinsics into the block, we keep them opaque so that they're always valid, right? It's not that I have a different client or different code. Okay, for these blocks handle this encoding, for this block handle this encoding, for this block handle this code. No. That in order to keep the blocks valid for all the history of the chain, we double encode them. Now, it could be that your client does not understand what the encoding was in the past. That's fine, as long as the blocks are valid, right? As long as the blocks have the information, it's fine, right? So the reason we bring this up is because when the blocks actually the extrinsics actually get included into the block, they're double encoded, right? Cool. Yep. Okay, so now I want to mention there's two different runtime APIs. So runtime API is where the client will call the runtime, right? There's two different APIs for building blocks, or for block building. One is actually building the block, executing a transaction one at a time, and the other one is importing a block, executing everything at once. So when you're a block builder and you're actually creating a block, you'll be using this block builder API. which has a function to apply extrinsic one by one. So basically, you'll initialize the block, you'll get your list of transactions, and one by one, you'll execute it, right? Is this valid? Is it not valid, whatever? And if a transaction doesn't execute well, you throw it away, put the new one in. You're trying to make a block, right? A block of all valid transactions. Now, this is slower, obviously doing it one by one. Like, you could, instead of batching it, but it's the only way you can basically make a block and ensure that you're not wasting much time. Like if one of those transactions were invalid, right? Then you would have to like rebuild the whole block and whatever. You're adding them in one by one, right? And you're building a block. Once you've created a valid block, oh wait, let me skip. Okay, so this is the idea. There's another API I'll talk about later where you can just import a block that you know is valid, but we'll go to that later. So let's talk about some terminology, right? So we've been talking about call and extrinsic and dispatch. These are all kinds of, how do you say, within the world of Substrate and Polkadot, all kind of the same, but they are different. And the reason why it gets confusing is because they're all just different parts of the same kind of process, right? So I might say, you can write a dispatchable function. You can create an extrinsic. You can write a call or whatever, right? Here's a sentence which uses them all together in a kind of cohesive thing. So users submit an extrinsic to the blockchain, which is dispatched to a pallet call or to a function call. Okay. So again, extrinsic is just a word that means something from outside, right? So the blockchain is like some container. Some messages come from the outside. That's an extrinsic. This message gets routed to a specific function, right? That's what is being dispatched. And then the specific function is being called is the call. That's why they're all the same, kind of, right? But anyway, just a terminology. So the reason I bring this up is because the next step, once we actually include a transaction into the block and we call apply extrinsic, what's actually happening is extrinsic dispatch. So apply extrinsic will say, okay, here's the call I want to have. And we have to remember, going back to lecture 4, is that the one? No, lecture 3. Going back to lecture 3, we have a call function which has palette index, call index, and parameters, right? So as a part of the apply extrinsic, I see this payload, and it's telling me, hey, call palette 5, call function 3. That is the dispatch, right? It is dispatching to this exact function call to this exact palette, right? So here, so here we'll collect from the payload which palette am I going to call, which call am I going to call, and which function parameters I'm going to use, and we'll basically route the message to the right place. If you did the Rust state machine, you should have remembered one of the steps at the end was you wrote the dispatch logic. You actually wrote how we have the enum, we can parse it and push it through. That's basically the same thing that's happening inside of Substrate, right? One thing we do though is, if you're familiar with Substrate at all, you know that every extrinsic has this thing called the origin. And we'll learn more about origin in the future. But if you notice here, actually going back to this, there is no origin in this payload. What happens actually is the blockchain itself is injecting the origin. It, through the validation, adds the origin to the payload and actually uses that as part of the function call. So even though you didn't include the origin in your extrinsic, we will add the origin to tell the function where the message came from, right? And normally, most extrinsics, this origin is just a signed message. So it's basically saying the blockchain got this big transaction, and I'm going to tell your function, here's the call, here's the parameters, and it came from this user. It's a signed message, right? That's basically what happened. But I will note here that the signature verification is happening in transaction pool. It's not happening in the extrinsic dispatch. So by the time it gets to your function, you're not dealing with signatures. You're just dealing with an address. Okay? Okay, and then function execution. Okay, so there's nothing really exciting about function execution. By the time we actually dispatch the call and we get to the actual function you want to call, it's just Rust, man. It's like there's nothing magical happening. It's literally you wrote a Rust function. It is a pub function with a name and it has some parameters. It's just executing the code. There's no magic there. It's just running a program, right? And in that program, you can do whatever you want. You can mint tokens. You can update your storage. You can destroy your chain, whatever. Whatever you write in that code, it will do. Now, all the time in this academy, we'll tell you, don't do this, don't do that. You can do whatever you want, man. You can literally write whatever code you want. We say don't do that because it will make your chain unsafe, right? If you do too much checking in the pre-validation of a transaction in the transaction pool, it'll make your chain attackable. So when we say all these do not do's, it's not that you can't do it, it's that you shouldn't do it. But then one of the things about being a substrate developer or being a runtime developer is you really have full power to do whatever you want, right? So, great power, great responsibility. I want to also mention here that the only reason some transaction is able to call some function in your Rust code is because of the dispatch, right? So in your code base could be hundreds, if not thousands of public functions, right? Public functions in your Rust code are not public to the world. They're just public in the sense of like making a Rust library, right? What actually makes your function callable by some user is the fact that there's a dispatch pipeline to call that function. If you do not have a dispatch pipeline to call that function, there's no way a user can call some function. So marking some function pub does not mean every user can call it. You actually have to expose it to the outside world through a dispatch, right? Okay. Anyway. Once you're actually executing the function, the most common thing you will see inside of that function execution is state updates, right? Like the whole thing about blockchain is just a database, right? So it has some logic and some checking, but ultimately you're updating the state of the blockchain. And so you might see some things like the first one here, this is a very low level. Our low level storage is SPIO, and you can basically set any key and value you want. So this key here is the try key, the try path, and this value is that value. And of course, in the background, it does all the magic to turn it into the right place, the Merkle tree, and put in the database. But this is some try key. This is that value. So this is the code. This is that system balances, whatever. That is that piece. But this is too low level. What we actually expose to you are beautiful APIs, which do all the magic for you. So if you were to do this, you would have to construct the key yourself. When you do this, we know which palette you're in, what your storage name is, and we automatically do all the hashing for you and make the key for you, right? So we handle that for you. And of course, when you actually go and call update storage, you're not writing to the computer directly. You're going through many layers. So you're the developer, you write some code. It first parses that through the runtime storage APIs. This has some storage overlay. Storage overlay is like basically like a memory. So it puts things in memory before it actually puts in the database, right? Then it goes to the Merkle tree. Then it goes to the key value database. Then it actually gets stored in your computer, right? So just calling, SPIO set this storage or this one will make your storage go through all of these layers, and you don't see them. It just happens in the background, right? Same with when you read. Yeah. Okay. And finally, as we mentioned, there's the block creation API. Once we've executed all the functions, we've built the block and it's valid. We wrapped it up. We then gossip it to the world. All the other chains are now importing the block, right? They have a brand new block. You're a valid block producer. They verified all the things in the header. You're actually importing the block. There's a simple API called execute block. And rather than doing things transaction by transaction, it executes the whole block as one. So either the whole block is valid or the whole block is invalid. There is no in between, right? So it's either all valid or invalid. And there's a nice API that does that. And it's a different runtime API. And yeah. And then of course, once a bunch of different users on the network have all imported the block and are updated to the latest state, they will then say, okay, this block looks valid to me. The author is correct. I'm going to vote and say, hey, this is a good block, right? And now we go back to grandpa, right? Right back to the header. A signature will be created for that block hash and propagated to the network. And everyone else is going to see the signatures. And we're going to be able to collect those signatures and wait for 2/3 plus 1 majority to be able to say this block is finalized, right? And then, yeah, and then let me see, final state verification. And then, yeah, you as a light client, you saw the transaction get in, you got notified in block. You saw the transaction get finalized, you got notified finalized, right? That might not be good enough for you. You may actually want to do one last verification. Did the state update the way I expected? So what you can do is another read storage with proof, right? You can check the events to see the extrinsic success, and you can check that your balance was updated correctly, right? And end to end here, we've shown you how you can do an entire end-to-end transaction with a light client at every point of the process, not trusting anybody, verifying everything yourself, using the peer-to-peer network, having the system work in a decentralized manner, right? Yeah, less trust, more truth. Okay, that's all. That is the end-to-end. We were able to take a light client. We were able to understand how to use the metadata, how to read the storage, how to create a transaction, how to submit it there, how to follow the transaction, have the nodes update it, how to get finalized, how to get the produced, etc. and then verify everything works. And this is the backbone of how we can create trustless systems. Okay, yeah, questions?
Hey, Marcin here. Easy question. What SP from SP API stands for?
Substrate primitives. Okay, so that's a great question. So when you use Substrate or Polkadot SDK, you're going to notice a few things. You're going to notice SP, what is it? SP, SC, S, or just frame, whatever. SC stands for Substrate Client. So all of the libraries in here, like if I go to SC CLI, if I go to Cargo Toml, SC CLI. Executor, it'll be SC Executor. So that's everything under Substrate Client. And then P is primitive. So SP API. SP Application Crypto. Yeah, so it's just kind of navigating. And when we get to the protocol track, we'll teach more about this. But that's the basic the breakdown. Okay.
One question. You mentioned like a few minutes ago about the having your function public without dispatch.
Yeah.
It would mean like the user like cannot call from outside, but it could be called by any other like modules, correct?
Any other logic inside of your code? Yeah.
Inside or like outside, it could be called by other applications, so it could be kind of like a vulnerability.
No, the public functions are only limited within your one binary, right? So within your WASM runtime, other parts of your code can call public functions, but your client can't call a public function of your code. The pub in Rust is talking about like when you're compiling code, like how you can use different code as library, right? Not that the function exists as WASM is exposed in a WASM call, right?
Thank you.
Yeah.
Yeah, go ahead.
Hey, Shawn, this is Satish here. I have a question on the block production side. So with VRF, we do have a situation that there could be more than one author creating a block at a given point of time.
Yeah,
like
sure.
Forking.
That's
So does
yep.
all the forks contain the same set of transaction, or can it be different set of transactions?
Definitely not. Like all the forks will definitely not contain the same transactions in the exact order or anything, because the way that it's propagated could be like I never even saw a transaction, or the order of the transaction could be different or whatever.
Yep.
That's not deterministic. Only once I have a block and the block has a certain order, that's where determinism starts coming in.
Mhm.
But it could be, there's multiple versions of a valid transaction or a valid, block.
Right. So in that case, like if some transaction get into a fork,
Mhm.
and if that fork has been gone away, so
Yep.
all the transactions will become invalid, or
No, but the transaction should then be included in the other.
or
thing.
that goes back to the transaction pool.
Yep.
Okay.
I mean, like it's how do you say this? Yeah, exactly. Again, it's not as simple as that, because a client could be managing many forks at once, right? And the transaction pool and the runtime, it handles like all these possibilities. So, it could be that from the viewpoint of a client, in this fork, this transaction is included. In this fork, it has not been included yet, right? So like it's just managing all those stuff. And this is again why you use Substrate, because you don't want to be the developer reprogramming all this stuff. Like all these things, we've done it for you already. You can just work on your product, right? Yeah.
Hi. So talking about the double encoding of the extrinsic, is it like, does it always sit as double encoded inside the data availability layer, or is it only a temporary thing that we do while transferring this extrinsic to the runtime?
So double encoding, it just comes up wherever there's an interface where we expect the two halves to change a lot. I don't mention it because it's like something that you have to worry about end to end. Like, practically speaking, we handle this for you. I only mention it because I wanted to show you that if you actually went and like I showed a lot of practical examples. If you went to the block and you're like, okay, let me look at the block, let me look at the extrinsics, let me see exactly what Shawn said. That there'll be one thing that you'll need to do, which is you'll need to decode the VEC-U8 into the extrinsic format to then see exactly what I have been doing. So it's not something that you should be super caring about. It's just something I wanted to show, like, if you actually went into the block and saw the list of extrinsics, you're one step away from seeing the real format. You need to encode it one more time into the extrinsic format.
Okay, so let's say I'm running a block explorer. I have an archive node. So would it be more efficient for me to like double decode the directly from the block, or ask the runtime API to give it to me straight?
No, you just decode it yourself. You as a block explorer, one of your jobs is to hold all the extrinsic formats, and then just to process that and decode it. It's super easy. Yeah. Like I would say, as a block explorer, you wouldn't even expose the double encoding to the user. You would just like, you know it would be there, but you would just show them the encoded extrinsic.
I guess one thing I just realized, but maybe it doesn't hurt to just ask. So like the transaction extensions, I guess I was a little bit confused when I saw that the runtime API was like exposing apply extrinsic, because it feels like the runtime API is also the one that's responsible for like the logic.
So runtime API is when the client calls the runtime. So you agree that when I submit an extrinsic, it goes to the client. And the transaction pool is also the client. Eventually, the client needs to be like, hey, run this transaction to the runtime. So if the client is calling the runtime, it's the runtime API. Right? So like at some point, the client is like, I don't know what the logic of the blockchain is. The runtime knows the logic of the blockchain. So here's the transaction. Please execute it for me.
Okay.
And then what's happening is like I'm executing it. So imagine this. Like imagine that there's a conversation between these two guys. It's like, hey, please execute this transaction. And then the runtime's like, okay, I'll do it. It goes quiet. Hey, client, update this storage. Okay. Hey, client, update this storage too. Hey, client, update this storage as well. And then it says, hey, I'm done. So the client doesn't know what's going on. The client is only hearing from it every time the host function is called. And it's saying, oh, like, hey, client, please verify the signature. Hey, client, please do this hash, right? Like all the things that the client needs to do. And then it says, I'm done, it was successful. And the client says, oh, successful. Then it's like, done. So the client is calling the runtime. Yeah, it's runtime API. It makes sense. I mean,
yeah.
Okay. Okay, cool. Yep.
So I have two questions.
Yep.
What is the use case for immortal transactions, especially when mortality, we can specify a very huge number?
Yeah, so there is an option. So that's great. So we talked about earlier, there's this era, and you can specify how long you want your transaction to be valid for. There is an option as a user, if you explicitly want to allow a transaction to be immortal, which means that it doesn't follow this era rule, you can do it. What is the purpose for it? I don't know if there's a lot of, off the top of my head, one practical purpose? Yeah, please.
Yeah, the purpose is basically like if you want to risk later on losing your funds with a replay attack, then please use an immortal transaction and let me know.
I think
okay? That's the only purpose.
I honestly believe, and I'm gonna agree with him. I honestly believe the immortal transaction exists the same as the null point or the null pointer thing. Like it's one of those things that was so easy to say, an option, some, none. Someone put none, like we just did it, and then none is the option, and it really is kind of like you should never use it, but it's just like, I guess with substrate being so unopinionated, it's unopinionated to the point of shooting your foot off, right?
Actually, there is a valid use case.
There's a use case? Tell me.
Yeah.
Tell me a good use case.
No, it's not good. So I think it can be done differently, but one use case is it's the only way to build a transaction without being connected to the chain. So without knowing the block hash is different than the genesis. So you need, if you use mortality, you need a block hash like current. Like the block hash we need now, and if the transaction is immortal, you don't need it. You can build it being offline. So
yeah, I think that's not a good. Yeah.
Yeah, it's not good, but it's the only use case.
There's no good use case really. I mean,
Yeah,
you
so
should
sounds
not.
like for the testnet it's good, but for the mainnet it's more dangerous than it is useful. So second question, I was just comparing.
Wait, sorry, pause. That's actually a really good point. One way it could be good is if I'm constantly spinning up a new test net, right? I can make a bunch of immortal transactions, which then are put in some script, which are then fired to the chain every time, right? So we never have. I guess
it's
the
very
error would never
unlikely
reset
that
though,
the
right?
genesis hash is the same.
Huh?
It's unlikely that the genesis hash is the same among.
Oh, you're right though. Yeah, that's a good point. Yeah. Okay. Never mind. But okay. Go ahead. Anyway.
Okay. Second question is regarding the implementation of Patricia Merkle trees. It looks like transaction pool is always going to be write heavy. So I was just comparing it with some database.
Transaction pool is always going to be write heavy. I don't agree with that statement. So why do you think, tell me why transaction pool is write heavy?
I mean to say not the queue part of it, but where the transactions are actually getting recorded for the first time. Later, they'll get processed and organized into multiple queues.
Transaction pool is not storing the transactions in a Merkle tree. Merkle tree is only for the runtime storage.
For the runtime storage.
So you don't need it for the transaction pool. Transaction pool just uses like in-memory database.
Got it. So for the runtime storage, instead of using Patricia Merkle trees, could you also comment comparing with LSM trees or some other data structures used in write-heavy database like Cassandra?
Right. So I don't know exactly about that one. And it's the same question about Merkle trees. But I can tell you this: does that write-heavy storage thing, does it allow us to create verifiable proofs, storage proofs?
Right, but then the complexity for fetching it would be higher, right?
Yeah, that's about the whole point. So again, my presentation is this: we know Merkle trees are slower for reading, slower for writing, but it is infinitely faster for verifiable proofs. And as a blockchain developer, our priority is not to make the fastest blockchain. I know some blockchains will convince you that is the priority of the world right now, to make the fastest blockchain. That is total bullshit. The priority we should make is a decentralized future where we can have verifiable proofs for the data we want to access. So the Merkle tree, and I guess Merkle tree does the same thing, but Merkle tree is the most obvious way of being able to very succinctly verify data exists in the chain. So any other alternative, I'm sure there are some, maybe has some benefits, but if it doesn't have light verifiable proofs, it's not going to be useful for our scenario.
Got it. And also, is it a trie or is it a tree? If it is a trie, what is the common prefix?
Yeah, so it is a trie, and the trie, there's lots of common prefixes. So the trie is all about, like, again, imagine that my key, let's go here. Imagine my key was like A, B, C, D, and I only have one key. In the most dumb version of a tree, you would create node A, connected to node B, connected to node C, connected to node D. Oh my God, I should have done less letters. And then here's my value. What a trie does is it knows that there's only one path here, so it just puts them all together as A, B, C, D, as one thing. So it's always a trie, and it's just a more efficient version of a tree.
So trie based on the transaction hash or the Merkle hash, like what is that prefix which is common between multiple nodes starting from root to the leaf?
I feel like you're asking me like I should know that there's something specific. It's not. It's a hashes. These are like hashes or things. They're.
I can take a bit this one. So storage keys. So there is nothing to do with tries and transactions. So transactions are not stored on tries or whatever. The thing that, so why use a trie in the runtime storage? The thing is that keys are not hashed directly. Let's put it that way. So the first part of the key is the name of the. For example, do a good thing for me. Put an account ID there. Yeah. Let's see that the encoded key. It's 26 AA 39 blah 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 whatever. Now change entry from system account to system another thing. No, use system, but whatever. You see that it's 26 AA 39 blah blah. It's still the same initial part. It's because in the trie, it's ordered by module, and so in this case, palette and entry. So actually, it's very useful because you can imagine that I'm only interested on balances palette, so I can verify the whole tree of balances without taking the rest.
Got it. Thank you.
Yep.
Okay. Coffee break. All right.
Sorry for the hijack.
Wait, that was my full thing. If you have any more questions, you can ask it in chat. You can let me know, find me in coffee or whatever, and we'll happy to answer. Again, this is just an overview, so you'll be learning about a lot of these topics throughout the rest of your time here. But this kind of shows you end to end how you can go from from a light client all the way to making a transaction, all the way to a block being finalized. It kind of encompasses everything and shows you kind of all these details why they matter, right? All right, cool. All right, thank you very much.